The first branch of physics that we're going to learn about this year is called mechanics. Mechanics is the branch of physics concerned with the motion of bodies under the action of a system of forces. And bodies is just a synonym for objects. It doesn't mean human bodies or something like that. And it comes from the Greek word mechane, which means machine. And the study of mechanics goes back all the way to ancient Greece with philosophers like Aristotle and Archimedes. The first topic we're going to learn about in mechanics is called kinematics. Kinematics is the branch of mechanics which describes the motion of objects without consideration of the causes of the motion. So we care about how things are moving and not why things are moving. And this comes from the Greek word kinema, which means movement. Okay, into the first lesson, which is called scalars and vectors. And the guiding question for this lesson is what's the difference between a scalar quantity and a vector quantity? So first, why don't we define quantity? In physics, a quantity is a property of an object that can be quantified by measurement. So the number of books on a bookshelf or the length of your pencil are quantities. You can count those, you can measure those. And we'll learn a lot of quantities this year. So instead of giving definitions that really don't make any sense out of context, let's look at some examples. So here are some examples of quantities that would be considered scalars. I don't know about you, I really like Skittles. And when you pour some Skittles out of your hand, maybe you get 5 Skittles. Maybe you get 18 Skittles. Maybe you only get 1 Skittle. Maybe the bag was empty and you get 0 Skittles. Right? The amount of Skittles that you get is a scalar. Another classic example of a scalar would be money. Right, in your pocket, maybe you have 42 cents, maybe you have $5, maybe someday you'll have $1 million. I guess not in your pocket, but you could have $1 million. And the amount of money that you have would be a scalar quantity. And another example that I like to use is music. And there are a lot of different aspects of music. I'm thinking about the volume at which you listen to some music. So sometimes you listen to music quietly. Other music you listen to in a more moderate volume. And sometimes you listen to music that you just have to blast. Right. These are all examples of scalars. And so to define scalars, we'll say that a scalar quantity has magnitude only. And magnitude means amount. So we talk about an amount of Skittles that you have or an amount of money that you have. Those are scalars. Okay, let's move on to vectors. Here's an example of a vector quantity. So let's say this is your house, a very lovely house, I might add, and you want to describe to me where the school is in relationship to your house. And you tell me that the school is 2 miles away. And, that's helpful information. But, the school could be 2 miles northeast of your house, or 2 miles southeast of your house, or 2 miles west of your house. And so I don't really know where the school is. I don't have enough information. In fact, the school is in the center of this picture, and, every place on that white circle is 2 miles away. So it's really not that specific to say 2 miles away. However, if we just add one extra bit of information, if we say that the school is 2 miles northeast, then I know exactly where it is. And the addition of the information about direction really helps out. Here's another example. Let's say you're driving on the Long Island Expressway in Comac, and I want you to tell me where you think you'll be in an hour. Well, it depends on a couple of things. First of all, how fast are you driving? Right, the speed limit is 55 miles an hour, but sometimes there's traffic and you're only going like 20 miles an hour, or sometimes if there's like an accident, you might even be, stopped. You're going 0. And so how fast you're going is going to matter. And what also matters is the direction that you're heading. Right, if you're traveling east, then maybe in an hour you end up in Riverhead. Right, but if you're traveling west, maybe you end up in Manhattan. Right, so where you end up really depends on 2 really important things: how fast you're going and what direction you're going. So let's define a vector. A vector is a quantity that has both magnitude and direction. And I hope that you can see in these 2 examples how important the direction information is. The second lesson in kinematics is about distance, displacement, speed, and velocity. The guiding question for this lesson is as follows. To most people, speed and velocity mean the same thing. Do they mean the same thing in physics? We're actually going to start with distance and displacement. Here's a happy little bee, and he's going to fly over that flower. And of course, he kind of buzzes around on his way there. And if we highlighted the path that the bee followed, in this case it's the green dashed line, we would know its distance. Right? The distance it traveled is represented by the length of that green dashed line. Another way we can represent how this bee traveled to the flower is by imagining an arrow that points from where the bee started directly to where the bee ended up. And this would be known as its displacement. Right? The length and direction of this arrow is the bee's displacement. And clearly the distance and displacement are different. They're different magnitudes. The distance line is much longer than the displacement line. Let's define these. The distance is a scalar quantity, and it's the length of the path traveled by an object. The actual path traveled, that green line. Displacement, which is a vector quantity, is the length and direction of an arrow originating at the object's initial position and ending at the object's final position. In other words, it's how far an object is from where it started. Right? Directly in a straight line, how far is it from where it started? And of course, the direction is important. Let's take a look at a couple of examples. Let's say one day you take the train into Penn Station, and you walk 7 blocks uptown, and then you walk 2 blocks across town to Bryant Park, and then you walk 7 blocks downtown to Herald Square. And we want to know your distance and your displacement. Well, you walked 7 blocks, and then 2, which is 9, and then 7, which is 16. Your distance traveled is 16 city blocks. But for your displacement, remember, we care about how far you are from where you started, directly in a straight line, and of course the direction, because it's a vector. So at Herald Square, you are 2 blocks away from Penn Station, and this red arrow represents that. So your displacement would be 2 blocks, and of course you are, looking at the map, southeast of where you started. Your displacement would be 2 blocks southeast. Here's another example. This is the track at the high school, and let's say one day during PE you have to run a lap, and you start at this yellow X, and you follow the blue path around the track, and you end up back at the yellow X. Again, we want to know the distance and displacement. So I hope you know this, you've run around the track before. The distance around the track is a quarter mile, or in metric units, it's 400 meters. So your distance is 400 meters, that's how far your leg actually carried you. But your displacement is very different. You started at the yellow X, and you're ending up at the yellow X. So how far are you from where you started? I mean, you are where you started. You are 0 meters from where you started. There isn't any arrow that you could draw between those 2 points because they overlap. So in this case, your displacement would be 0. And I think this brings up the point about, in real life at least, what's more important, distance or displacement? And I think in this case, distance more accurately represents what you did. You ran 400 meters. But in physics, and also in real life sometimes, displacement is also a very important number. And we'll discuss that more in class. Right, on to speed and velocity, and this one's a little bit simpler. The velocity of an object, which is a vector quantity, is the rate of change of position. So it's how quickly an object moves from one place to another. And for this car, we know it's moving 90 kilometers per hour, and it's heading toward the east. So we would say that its velocity is 90 kilometers per hour east. It's a vector quantity, so it has magnitude, 90 kilometers per hour, and direction, east. Okay. Speed is a scalar quantity, and it's just the magnitude of the object's velocity. So we don't care that it's traveling east. All we care about is how fast it's moving, and its speed is 90 kilometers per hour. And that's basically it. The third lesson in kinematics is average velocity, part 1. The guiding question for this lesson is, how is average velocity different from instantaneous velocity? Well, instantaneous velocity is the velocity of an object at one specific moment. The speedometer in your car shows you your instantaneous velocity. So for instance, car A at this moment is traveling 0 miles per hour, car B at this moment is traveling 55 miles per hour, and car C is traveling 130 miles per hour. So we know at these specific moments how fast the cars are going, but we don't know if these cars are in the process of speeding up or slowing down. All we know is what's happening at this one very specific moment. Let's get into average velocity, and first let's see how displacement affects average velocity. Imagine we have a foot race between Isaac and Gottfried. They're both going to run for 10 seconds, and we'll see who runs farther. Isaac runs 40 meters, and Gottfried runs 25 meters. So who had the greater velocity, the greater average velocity? Well, if Isaac ran farther in 10 seconds than Gottfried, then on average, he must have been going faster. He wasn't necessarily going faster than Gottfried at every specific moment, but over the course of the entire 10 seconds, he was moving faster. We would say that average velocity is proportional to displacement. Take a moment and carefully draw that symbol there. We're going to use that a lot this year to represent proportional to. And we would say that this is a direct relationship. The more displacement you have, all things being equal, the faster you're moving. Now let's see how average velocity and time are related. Let's imagine another foot race between Nicola and Thomas. This time they're both going to run 30 meters, and we'll see who runs it in less time. Nicola takes 15 seconds, and Thomas takes 20 seconds. And I'll ask the same question, who had the greater average velocity? Well, if Nicola ran the race faster, meaning in less time, then he had the greater average velocity. And again, Thomas could have been running faster than him at a couple of moments, but over the course of the entire 30 meters, Nicola was faster. We would say that average velocity is proportional to 1 over time. This is an inverse relationship. The more time it takes you to run a race, the slower you are going. Average velocity is a vector quantity, and it's the rate of change of position during some interval of time. We've seen that it's directly proportional to displacement and inversely proportional to time. The equation we can write for average velocity is displacement divided by time, and we'll see direct relationships in the numerator and inverse relationships in the denominator many, many times this year. We normally write it like this: V bar equals d over t, where V bar represents average velocity, d stands for displacement, and t stands for time. Let's take a look at a couple examples. A train travels 450 miles in 6 hours. What is the magnitude of the average velocity of the train? Notice I'm asking for the magnitude of the average velocity. We don't know which direction this train is traveling, and we don't care. So we'll use our new equation, V bar equals d over t, and we can substitute in our 450 miles in our 6 hours, and you should double check this math to make sure that I know what I'm doing. I calculated this to be an average velocity of 75 miles per hour. Of course, the train speeds up sometimes, it slows down sometimes, it stops sometimes, but on average, during the 6 hours, it's traveling 75 miles per hour. Let's take a look at one more example. A student runs a 100-meter race at an average velocity of 7.5 meters per second. How long will it take them to finish the race? Well, we can use the same equation, and we can substitute it in our velocity and our distance. And this time we're solving for time, so we can say that we cross multiply, we can say that we multiply both sides by t. Either way, we end up with t times 7.5 meters per second equals 100 meters. And when we divide by 7.5 meters per second, we find out that the time it took the student to run the race is 13.3 seconds. Let's address average speed briefly. We've seen that speed and velocity are very closely related, and since speed is just the magnitude of the velocity, they're quantified using the same equation. However, if we're talking about average speed rather than average velocity, then v bar stands for average speed, d stands for distance, not displacement, and t, it still stands for time. The fourth lesson in kinematics is about acceleration. The guiding question for this lesson is, how is acceleration related to velocity and time? Acceleration is a vector quantity, and it's defined as the rate of change of velocity. We can say that acceleration is the change of velocity divided by time. We normally write it like this: a equals delta v over t, where a stands for acceleration, delta v stands for velocity, and t stands for time. I'd like to talk about delta for a moment. I know you've seen it before, I know that you know it means change of, but it's important to make sure we know how to calculate it precisely. So when determining the change of a quantity over time, we always subtract the initial value from the final value. In other words, you take the final value minus the initial value. Like this, delta x equals xf minus xi, final minus initial. And when you do that, the sign, whether the answer is positive or negative, on your answer will show you whether the quantity increased or decreased. Let's take a look at a couple examples. Money is a great example. We all know about money. So let's say you leave the house one morning with $10 and you come home with $4. Right? I'm sure you could tell what happens, but let's look at it technically. Your delta money would be your final money minus your initial money. So $4 minus $10 is negative $6. So the amount that your money changed is $6, and it's negative, which means you have less money than you started with. You have $6 less than you started with. Let's take a look at another example. Still money. The next day, you leave the house with those same $4, but you come home with $19. Right? So your change in money would be your money final minus your money initial, which would be $19 minus $4, and we get positive 15. Right? Over the course of the day, you acquired $15 somehow. Right? You have 15 more dollars than when you started. And so if we carefully do final minus initial, we'll get the sign in addition to the amount, and that's very important for us. All right, let's get back to acceleration. The dragster in the video accelerated from rest, which is 0 meters per second, to 135 meters per second in 5.23 seconds. Let's figure out the magnitude of the dragster's acceleration. Notice again, like we've seen before, I'm asking for the magnitude of the acceleration. We don't care what direction it was accelerating for right now. So we'll start with our equation, as always, A equals delta V over T. And I like to write out sometimes specifically what delta V means, right? It's VF minus VI, and we can substitute in what we know. 135 meters per second minus 0 meters per second, the final, minus the initial, divided by 5.23 seconds. You should follow along in your calculator and double check this. I get the acceleration to be 25.8 meters per second per second. Let's talk about these units before we go any further. So we left it as meters per second, but you're not always going to see it like that. In fact, you'll rarely see it like that. If you take meters per second and divide it by seconds, we can say that's the same thing as meters per second over seconds over 1. You could put anything over 1. And then, instead of dividing by a fraction, we can multiply by its reciprocal. You might know this as keep, change, flip, but it's called multiplying by the reciprocal. So m over s times 1 over s. And when we multiply those two fractions across the top, we get m times 1 is m, and s times s is s squared, and so we end up with meters per second squared. The units we'll usually see for acceleration are meters per second squared. But I like meters per second because it kind of describes more what happened. So the dragster started off at 0 meters per second, and then each second it gained 25.8 meters per second of velocity. So after 1 second, it was going 25.8 meters per second. After 2 seconds, it was going 51.6 meters per second. And you could just keep adding 25.8, well, at least 5 times, and then, there's a little bit more. Let's take a look at another example. A Boeing 737 touches down with a speed of 80 meters per second and comes to a complete stop in 35 seconds. What was the acceleration of the airplane while on the runway? We'll start with the same equation, and we'll do delta V like we said. It's the final value minus the initial. And since the airplane was stopping, its final velocity is 0 minus its initial velocity of 80. And so what we end up with is a negative acceleration. We get negative 2.3 meters per second squared. So each second, the velocity changed by 2.3 meters per second, and the negative sign in this case is telling us that the velocity is being reduced by 2.3 meters per second every second, from 80 all the way down to 0. The fifth lesson in kinematics is the second part of average velocity. We're going to start by taking a look at a launch of the space shuttle, and it's sped up to save a little bit of time. And you can see in the bottom right, they give you a bunch of data about the flight of the shuttle. You can see its altitude and its speed, and we're just going to watch for a moment. You'll see that when the shuttle reaches a speed of about 3,000 miles per hour, the solid rocket boosters will detach, and that's where we're going to leave it. The guiding question for this lesson is, what is another way to calculate average velocity? So if we look at that shuttle launch, from launch until the separation of the solid rocket boosters, the Space Shuttle Discovery accelerated from rest to about 3,000 miles per hour, which is 1,340 meters per second, in about 2 minutes and 6 seconds. From that data, we could definitely calculate the acceleration if we wanted to, but we don't particularly care about that. Could we calculate the average velocity? Well, v bar equals d over t, and we have the time, but we don't really know the displacement. And maybe we can go back to the video and look at the data and see, but we're not going to do that. There's another easier way for us to calculate the average velocity. For an object undergoing uniform acceleration, the average velocity is the average of the initial and final velocities, literally, the average. Uniform means not varying or changing, staying the same at all times. So if something is accelerating at a constant rate, we can calculate the average velocity in this way. So for the example of the space shuttle, we can write the equation v bar equals vi plus vf over 2, literally the average of two numbers, just like you average a test. And note, this equation is not on your reference table, but it is a valid equation and very helpful at times. We can plug in our numbers, 0 meters per second to begin with, and 1,340 meters per second at the end, divided by 2. We can find that the average velocity of the shuttle was 670 meters per second. It's as simple as that. Let's take a look at one more example. So let's say this car was traveling 18 meters per second when it began to slow down, and it came to a complete stop at the red light. What was the average velocity of the car? Well, average velocity is the vi plus vf over 2, and 18 meters per second plus 0 over 2 is 9 meters per second. That's it. The sixth lesson in kinematics is called uniform accelerated motion, and the guiding question for this lesson is, what are some mathematical expressions that we can derive to relate the properties of an object's motion? I want to start with a disclaimer. I'm going to show you how we can take the three equations that we already know and manipulate them and combine them to form three new equations so that we can see different ways that displacement, velocity, acceleration, and time are related to each other. And these equations are very, very important. But what's not super important is that you fully understand where they come from. You certainly don't have to be able to recreate these derivations on your own. I think it's something that's important for you to see. So don't write down anything that isn't in a blue box. You'll see. And if you don't understand every step of the way, don't worry about it. Okay? Just try to follow along the best you can. Write down the equations when they get boxed in blue, and then we'll use the equations in class, and you'll see how they work, and that's what's really important here. Okay? So let's start with UAM equation number 1. We've seen this equation before. This is A equals delta V over T. And this one's easy. We're just going to rearrange this equation a little bit. So let's multiply both sides by T, cross multiply in other words. And then we're going to add the initial velocity to both sides. And that's it. I want to rearrange this so it looks better. But that's what we end up with. VF equals VI plus AT. This is really not even really a different equation than A equals delta V over T. It's just rearranged, but it's a good place to start. All right, on to UAM equation number 2. I hope that you recall that there are two equations for average velocity, d over t and vi plus vf over 2. And since they both equal v average, we could say that they equal each other. If a equals b and a equals c, then b equals c, right? So let's do that. Let's set these two equations equal to each other. And now let's multiply both sides by 2. And so we end up with the 2 over here. And then let's subtract vi from both sides. And I want to do that so that we get the vf all by itself, because we just learned an equation for vf. Right, vi plus at. So we can replace the vf on the right with vi plus at. Right? And we want to get rid of vf. What if we're looking at a situation where an object is accelerating from one speed to another, but we don't know how fast it ends up going, but we still want to know maybe how far it goes. Right? We've gotten rid of vf. That's our goal. So now let's combine the vi's by adding a vi to both sides. And I don't like that t in the denominator, so let's multiply everything by t. So we get 2vit plus at squared now. And let's get rid of these 2's. Let's divide everything by 2. So those 2's go away. And now we're just kind of cleaning up a little bit. We get d equals vit plus 1/2 at squared. That is UAM equation number 2. Okay, on to the final one. Okay, so we'll start with this equation again, a equals vf minus vi over t. And let's take a look at rearranging this a little bit. So let's multiply both sides by t, or cross multiply, and then let's actually divide by a. Right, I want an equation for t, in this case, t equals vf minus vi over a. And now let's look at UAM equation number 2, the one we just found. This is going to look ridiculous. It looks terrible. Just follow along. UAM equation number 2 has 2 t's in it, and now we have an equation for t. Right? We could replace any t we see with vf minus vi divided by a, and that's exactly what we're going to do. We're going to take that whole term and replace the t's with vf minus vi over a. So those are going to go in right there, and that's going to that looks like this. Right? And we're going to clean this up. We'll just get right into it. Let's distribute that vi into the vf minus vi, and let's square that term on the right. Okay, so when we do that, we get this mess. Don't worry, we're going to clean this up. Look at the term on the right. We have 1/2 a, and then we have over a squared. So the a and the a squared, one of the a's and the a squared cancel out, so that's cleaner. And now let's multiply the whole equation by a. So we get ad on the left, and those a's in the denominator disappear. That's a little bit cleaner. Okay, let's get rid of the 1/2, so we can break that term out of the parentheses over there. So to get rid of 1/2, we could multiply everything by 2. Right, so every term is going to get a times 2, and the 1/2 disappears. This looks terrible, but look at this. We have a positive 2 VIVF and a negative 2 VIVF. Those are gone. Okay. Also notice we have a negative 2 VI squared and a positive 1 VI squared. We can combine those. Right? That becomes just negative 1 VI squared. We're almost done. Let's add that VI squared to both sides. And now we're done. We're just going to rearrange this. We get the equation VF squared equals VI squared plus 2AD. That is our third UAM equation. So I hope you've written all these down. This lesson is about Newton's laws of motion. This is the first lesson in the dynamics unit. Dynamics is the branch of mechanics that's concerned with forces and their effect on motion. Let's start by talking about Isaac Newton himself. He was an English physicist and mathematician. He was born in December of 1642 and lived until March of 1726. He was educated at Cambridge University, and he was known for quite a few things. He developed the mathematical field of calculus. He was the president of the Royal Society of London, which is an elite organization of British scientists. And he was appointed the Master of the Royal Mint of England. What's important to us is that, among other things, he studied gravitation and its effect on the orbit of planets. In 1687, he published in Latin a book titled Philosophia Naturalis Principia Mathematica, which translates to The Mathematical Principles of Natural Philosophy. This is often just referred to as the Principia. It is widely regarded as one of the most important works in the history of science. Upon his death, Newton was buried at Westminster Abbey in London. Let's take care of some definitions. First of all, mass. This is a scalar quantity, and it is a fundamental measure of the amount of matter in an object. Next, we'll talk about force. This is a vector quantity, which means it has direction, and this can be described as an interaction that may result in the change of motion of an object. In other words, it's a push or a pull. There are 3 laws of motion as defined by Isaac Newton. We will refer to them as inertia, F equals ma, and action-reaction. Let's start by taking a look at Newton's first law. Newton writes, "Every body perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon." You might not really get what that means, but it makes a lot of sense. Newton is saying that an object sitting at rest on your desk is not going to start moving for no reason. Something would have to push or pull it, right? Something would have to exert a force on it. Likewise, without something like friction or air resistance or other objects to collide with, a moving object keeps moving at a constant speed indefinitely. In this video, we are looking at a crash test of a car. And you can see even though the car stops, the dummy keeps moving, right? It keeps moving at least until forces are exerted upon it, right? Forces are exerted upon its chest by the steering wheel and its head by the windshield. It's very important to understand the relationship between inertia and mass. The more mass an object has, the more resistant it is to a change in its motion. This means it has more inertia. Inertia is a property of an object that resists a change in motion. More mass is more inertia. Here's a video I took of me flicking a paper cup. On the left, the cup is empty. On the right, the cup is full of quarters. Each time I flick them with basically the same amount of force. The cup on the right, which is much more massive than the cup on the left, resists a change in its motion a lot more. Right? The cup on the right has more inertia than the cup on the left. The cup on the left, being so light, is very easy to change its state of motion, or in this case, its state of rest. Okay, let's move on to Newton's second law. Newton writes, "The alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed." Let's take a look at this first section first. Newton is telling us that acceleration, which is what he's describing as the alteration of motion, is directly proportional to the force. He also tells us that acceleration is inversely proportional to the mass. If we put these two relationships together, we get an equation for Newton's second law. A equals F net over m. We'll talk about what that net means a little bit later. This is commonly written as F net equals ma, and that's why we refer to this law as F equals ma. On your reference table, this equation is in the form A equals F net over m. Okay, let's take a look at this second part. It says that the alteration of motion is made in the direction of the right line in which that force is impressed. This is just a fancy way of saying that the acceleration of an object is always in the direction of the force that is causing it. The acceleration is always in the direction of the force that is causing it. Let's take a look at the units that we get from this equation. So we have the equation F equals ma. M is mass, and it is measured in units of kilograms. A, of course, is acceleration, and it's measured in units of meters per second squared. F is force. If we multiply kilograms times meters per second squared, nothing really combines or cancels out. We end up with kilogram meters per second squared. This is defined as a Newton. Right? The unit for all forces is newtons. Let's take a look at an example of a problem involving Newton's second law. A 30-kilogram child on a swing is pushed by an adult with a force of 120 newtons. What is the acceleration of the child while the adult pushes? We'll answer this problem like we do any other problem. We'll write down the equation that we're going to use. We can substitute in the information that we know, 120 newtons over 30 kilograms. We would find that the child's acceleration is 4 meters per second squared. Now let's take a look at Newton's third law, action-reaction. Newton writes, "To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal, and directed to contrary parts." What we care about is this second part. What Newton is saying is that when two objects interact, they each experience a force. These forces have the same magnitude, and they have opposite direction. Here's a video of kind of a kooky physics professor on a skateboard with a fire extinguisher. When he pushes down the handle to expel gas out of the fire extinguisher, the gas is pushed sort of toward us. Right? In turn, the gas kind of pushes the fire extinguisher, and of course, the professor holding it, away from us.
4, 3, 2, 1.
This is a really great example of action-reaction as described by Newton in his third law of motion. The second lesson in the dynamics unit is about gravity and weight. Newton's law of universal gravitation tells us that the gravitational force of attraction between two objects is directly proportional to the product of the masses of the objects and inversely proportional to the square of the distance between their centers. So this part says that Fg, the force of gravity, is directly proportional to m1 times m2, and this part tells us that Fg is proportional to 1 over r squared. If we put these together and include a constant, big G, we get the equation for the force of gravity. It's Fg equals g m1 m2 all over r squared. Fg stands for the force of gravity, m stands for mass, r is the distance between the centers of the objects, and g is the universal gravitational constant. You can find this value on your reference table. It's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Let's see how gravity and Newton's third law are related to each other. When two objects are attracted by the force of gravity, the forces they each feel are equal in magnitude and opposite in direction. Let's take a look at a pretty extreme example. Here's the Earth, and here's an apple. Let's pretend the apple is near the Earth's surface. The apple feels a force down due to the Earth. Newton's third law tells us then that the Earth must feel a force up due to the apple. Not only does the Earth feel a force up toward the apple, the forces are equal. The apple and the earth both feel the same force. How is this possible? Well, the forces are equal, but the apple has a very, very, very small mass compared to the earth. Therefore, the apple experiences a large acceleration. Because the mass of the earth is so great, the acceleration of the earth is pretty much imperceivable to us. So, though they both feel the same amount of force, they don't both react to that force the same amount. Let's take a look at an example of the gravitational force. What is the gravitational force of attraction between Earth and the Sun? Well, I need to tell you that the mass of the Sun is 1.99 times 10 to the 30 kilograms. Everything else we need to know is on your reference tables. As always, we'll start with the equation, Fg equals g m1 m2 over r squared, and we'll plug in all the information that we know. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and the distance between the Earth and the Sun is 1.5 times 10 to the 11 meters. If we carefully do all of that math, remembering to square the distance between the Earth and the Sun, we should find that the force of gravity between the Earth and the Sun is 3.5 times 10 to the 22 newtons. Please take a moment and see if you can get the same answer plugging those numbers into your calculator. Let's take a look at how two objects of different masses are both affected by the Earth's gravitational field. Here's the Earth, and here's that apple again. That apple feels some force down towards the Earth. And here's a skydiver. He also feels some force down toward the Earth. We're going to take a look at these simultaneously. So for any object, the force that they feel is equal to the product of their mass and acceleration. In this case, we know that the force these objects are feeling is the force of gravity. We also know how to calculate the force of gravity, right? Big G times the mass of the object times the mass of the Earth divided by the distance between the objects and the Earth squared. If you look at both of these, in each case, there's a mass in common on either side of the equal sign. We can cancel those out. On the left, we can cancel out the mass of the apple, and on the right, we can cancel out the mass of the skydiver. In both cases, this leaves us with the acceleration of the objects as big G times the mass of the Earth divided by the distance between the objects and the Earth squared. It should not surprise you that two objects, even of different masses, both experience the same acceleration near the surface of the Earth. Let's look at this in more detail. This quantity is what we define as little g. Little g is equal to big G, the universal gravitational constant, multiplied by the mass of the Earth, divided by the distance between objects that are near the surface of the Earth and the center of the Earth. This is essentially the radius of the Earth. If we plug in those values, we find that, surprise, surprise, the value of little g is 9.81 meters per second squared, or 9.81 newtons per kilogram. If we call it meters per second squared, we're defining this as the acceleration due to gravity. If we call it newtons per kilogram, we're defining this as the gravitational field strength. Unless the object is actually accelerating because of gravity, we are going to say that g equals 9.81 newtons per kilogram. Here again is the equation for the force of gravity between the Earth and some object near the surface of the Earth. All this stuff here is the same as little g, so we can actually rewrite this equation as Fg equals the mass of the object times g. Let's clean this up a little bit. Here we have two equations, both for Fg. This equation describes the gravitational force between any two masses anywhere in the universe. We're going to refer to this equation as the equation for gravitational force. This equation here describes the gravitational force between Earth and an object near its surface. We're going to describe this equation as the equation for weight. Let's take a look at an example of a weight problem. What is the weight in newtons of a 75 kilogram high school student? Well, we'll start with the equation Fg equals mg, plug in our givens, 75 kilograms and 9.81 newtons per kilogram. We'll find that a 75 kilogram high school student weighs 736 newtons. The third lesson in dynamics is about free body diagrams. We will often be examining objects that have multiple forces acting upon them. In these cases, we will draw free body diagrams, or FBDs. These are used to visualize and organize the information you know about the forces acting upon an object, or a body. There are some rules to how we draw these. First of all, every object is portrayed as a square or a rectangle. This is a diagram, not a drawing. Second, if the object is on a surface or an incline, you have to include that in your diagram, much like in the example above. Third, forces are vectors, and vectors are represented by arrows. These vectors, these arrows, should begin on the object or at its center and point away in the direction of the force. All vectors must be labeled. We have to know which is which. Finally, only draw forces on an FBD. Do not include acceleration vectors or velocity vectors. Let's take a look at an example. During a tug-of-war, a 10 kilogram rope is pulled left with a force of 50 newtons by team A and pulled right with a force of 80 newtons by team B. What is the acceleration of the rope? Well, step one is to draw the object. This doesn't look very much like a rope, but that's okay. This is a diagram, not a drawing. You'll see that oftentimes we write the mass of the object inside the box. The second step is to draw and label all the forces acting on the object. In this case, we have two: the force of team A to the left and the force of team B to the right. These forces will always be labeled F, but they will have different subscripts. Sometimes they have specific subscripts that we will always use. Other times you can make up your own. In this case, A and B. Step 3 is to label the magnitude of the forces if and when we know them. In this case, we know what both forces are from the very beginning, 50 newtons and 80 newtons. Other times, You'll calculate one of these forces as some future step of a problem, and when you do, you should add that magnitude to your diagram. And finally, we should use Newton's second law to finish the problem. Newton's second law tells us that A equals F net over m. The net force, which we haven't really talked about before, is either the difference between two forces that are in opposite directions, or the sum of two forces that are in the same direction. In this case, F net is 80 newtons minus 50 newtons, and we put that over the 10 kilogram mass. When we finish this calculation, we find that the acceleration of this rope is 3 meters per second squared. Since that is a positive answer, that means that the acceleration is in the direction of the force from team B. Let's take a look at an example of an object on a surface. A 5 kilogram crate on a frictionless surface is pulled to the right with a force of 25 newtons. What is the acceleration of the crate? Well, step 1, draw the object, and in this case it's on a surface, so we'll draw a line to represent that. Step 2 is to draw and label the forces. Well, there's an applied force to the right. This is an abbreviation you'll see many times. We use a lowercase a to abbreviate applied force. This just means any old force that someone or something happens to be exerting on an object. The force that we left off of the previous example, but that I want to include here, is the force of gravity. We're going to assume that any object is on Earth, unless otherwise stated, in which case this object is feeling a force downward toward the center of the Earth. Step 3 is to label the magnitude of the forces if and when we know them. Well, we know that the applied force is 25 newtons, and if we do a little calculation on the side, we can find that the weight of this object is 49 newtons. The final step is to use Newton's second law to finish the problem. We have A equals F net over m, and in this case, horizontally we only have one force, the applied force, so I guess we could write 25 newtons minus 0 newtons. If we finish this calculation, we find that the acceleration of this crate is 5 meters per second squared. What about the vertical forces involved in this problem, or the vertical motion? Well, this object is on the surface and is being dragged to the right. It doesn't have any vertical motion. It's not accelerating up or down. Let's take a look at what we find if we apply Newton's second law to the vertical forces and motion of this object. So we know the acceleration is 0, and we have a force down of 49 newtons and up of 0 newtons. But something doesn't look quite right here. This equation doesn't work out. What's going on? Well, it turns out that we're missing a force. According to Newton's third law, if the weight of the crate is pushing down onto the surface, then the surface must be exerting a force upward on the crate. We call this the normal force. The normal force is a reaction force that's exerted by a surface, and it's directed perpendicular to the surface. Let's look at Newton's second law again with the normal force in mind. We know that this object is still not accelerating up or down, so we can still plug in 0 for the acceleration. If we cross multiply and then solve for Fn, we find that the normal force in this case is equal to 49 newtons, just like the weight. That's not a coincidence. Again, Newton's third law should tell us that the forces between the crate and the surface are equal in magnitude, in this case 49 newtons, but directed in opposite directions. For any object on a horizontal surface, the normal force is going to be equal to the weight. And that's it for this lesson. There's no summary this time. This lesson is about friction. We often talk about friction as a negative force that must be overcome, but a world without friction is a dangerous place. Friction is a force that resists the relative motion of solid surfaces against each other. It's a reaction force. This means that without motion, or a net force that could cause motion, there is no friction. It's also a contact force. That means it exists at the location where the two surfaces are in contact with each other. The magnitude of the force of friction is directly proportional to the magnitude of the normal force. The more the surface pushes against the object, the more they sort of stick together. In the video on the left, I'm pushing the book horizontally. This means the normal force is simply the weight of the book. There is some friction, but the book slides relatively easily. In the video on the right, I am pushing down on the book in addition to pushing it forward. This greatly increases the normal force, and therefore also greatly increases the friction, making it much harder to slide. We can write that Ff is proportional to Fn. The force of friction also depends on what the materials are made of. Rougher surfaces tend to have more friction, and smoother surfaces tend to have less friction. This is quantified as the coefficient of friction, which is an experimentally determined value that is the ratio of the friction force and the normal force between two contacting surfaces. The abbreviation for coefficient of friction is the Greek letter mu. Coefficient of friction is a ratio of two forces, so it would be like taking something like 5 newtons and dividing it by 50 newtons, which would give us 0.1, but it would give us 0.1 what? Turns out coefficient of friction has no units. You can find the coefficients of friction for various pairs of materials by looking at your reference table. You'll see that there are two types of coefficients of friction, kinetic and static. Static friction is the type of friction that exists between two surfaces that are at rest relative to each other. This is the type of friction that makes it difficult to start sliding an object. It's important to note that when you calculate static friction, the value you determine from the equation is the maximum possible static friction. It's not necessarily the amount that's acting on the object at that moment. Kinetic friction is the type of friction that exists between two surfaces that are moving relative to each other. This is the type of friction that either makes it difficult to keep something moving, or slows down an object that is already moving. Let's take a look at an example of static friction. What is the maximum force of static friction between a 15 kilogram block of steel on a steel table? We'll start by drawing a free body diagram. We know we have the weight, Fg, and the normal force, Fn. We can calculate that the weight is 147 newtons. This means that the normal force is also 147 newtons. Now we can calculate the friction. We can look up the static coefficient of friction for steel on steel from the reference table to be 0.74. If we multiply that by the normal force, we find that the force of friction is 109 newtons. But remember, this is the maximum friction. If we only exert an applied force of 50 newtons, the static friction as a reaction force is only 50 newtons. If we exert a force of 109 newtons, the reaction force will be 109 newtons. However, if we were to exert an applied force of 110 newtons, the static friction as a reaction force could only be 109 newtons. This would result in a net force that would cause the object to start accelerating, which would then turn into a kinetic friction problem. Now let's look at kinetic friction. If an applied force of 110 newtons is causing a 15 kilogram block of steel to slide across a steel table, what is the acceleration of the block? Again, we'll start with the free body diagram. We know the weight is 147 newtons, the normal force is 147 newtons, and now the applied force is 110 newtons. We can look up the kinetic coefficient of friction for steel on steel from the reference table and calculate that the force of friction is 84 newtons. Now we just have to apply Newton's second law. The net force will be the difference between 110 newtons and 84 newtons, which gives us 34 newtons over 15 kilograms for an acceleration of 2.3 meters per second squared. And now, a message about surface area from Bobby of Flipping Physics.
Friction typically does not depend on surface area. In other words, because these two blocks are equal in mass, even though the top block has a larger contact surface area, they will have the same force of static friction. This is because pressure, which equals force divided by area, will decrease proportionally as the contact surface area increases, and the force of static friction will remain the same.
Oh, right, that makes sense. So this one, which has a larger contact surface area, has a smaller pressure, and therefore the force of friction in both cases will be the same.
Thanks, Bobby. This lesson is about vector addition. Remember that a vector is a quantity that has magnitude and direction, and we've already seen that we represent these with arrows. The length of the arrow represents the magnitude of the vector, and the direction of the arrow represents the direction of the vector. When adding vectors, the vectors that are being added together are called components, and the vector that you end up with is called the resultant. Let's look at a case where there's 0 degrees of separation between the two vectors that we're adding. So here's some object, and here are two forces acting on it. It would be easier to see the 0 degrees of separation if I drew these right on top of each other, but then we wouldn't really see both vectors. I still hope you can imagine that there's 0 degrees of separation between the directions that these two forces are pointing. If we combine these, we end up with a net force that is just the sum of F1 and F2. And that's what happens at 0 degrees of separation. The resultant is simply the sum of the components. What's also true about 0 degrees of separation is that this results in the maximum possible resultant. There's no other orientation of F1 and F2 that would give us a greater resultant. Now let's look at the opposite, 180 degrees of separation. So here's an object, again, with two forces on it. Here, I think it is more obvious that the separation is 180 degrees. Since the forces are in opposite directions, the net force is just the difference between the two forces. And that's always going to be true when the forces are 180 degrees apart. The resultant is simply the difference of the components. And 180 degrees of separation gives us the minimum possible resultant. There's no other way we could combine these two vectors and end up with a smaller resultant. Now we'll look at 90 degrees of separation. Let's imagine that this boat is trying to cross a river. It's heading north at 12 meters per second. This means that it's getting 12 meters closer to the opposite shore each second. At the same time, the river is flowing downstream toward the east at 5 meters per second. These two velocities are going to combine to give us the resultant velocity of the boat. Here's where we introduce the parallelogram method. This is a very useful and not too complicated method outlined by Isaac Newton about how to combine vectors. Here are the rules. First of all, the component vectors must originate at the same point, and you can see here they do. They both start on the boat. The next thing that you do is draw dashed lines from the tips of the arrows in order to create a parallelogram. In case you don't remember what a parallelogram is, it's a four-sided shape in which opposite sides are parallel to one another. We can draw these dashed lines to create a parallelogram. Once that's done, the resultant is just the diagonal of the parallelogram that's originating at the same point as the components. So there's our resultant. Since the two component velocities are perpendicular to one another, we end up with a couple of right triangles. This means that we can use the Pythagorean theorem to determine the magnitude of the resultant. So we do a squared plus b squared equals c squared, and plug in our 12 meters per second and our 5 meters per second, and we'll find that the resultant velocity is 13 meters per second. Finally, let's look at what happens at any other angle of separation. Well, for this, we'll also use the parallelogram method. So we want to make sure that the components originate from the same point. We want to draw dashed lines to create a parallelogram, just like that. And then we want to draw the resultant that is the diagonal of the parallelogram. How can we determine the magnitude of this resultant, though? It looks like one of those angles is pretty close to 90 degrees, but we can't be sure of that, so I don't think it's safe to use the Pythagorean theorem. In fact, the only way we can figure out the magnitude of the resultant is if we use a scale diagram. Sometimes you'll be given the scale of a diagram, other times we have to figure it out ourselves, which is what we'll do here. Let's measure the length of the 20 Newton force. It's 10 centimeters for a 20 Newton force, and we can set up a proportion. If 10 centimeters is 20 newtons, then 1 centimeter is how many? Well, it would be 2. This means that we think our scale is 1 centimeter equals 2 newtons. Let's confirm that by looking at the 13 Newton force. The 13 Newton force is 6.5 centimeters long, and setting up a similar proportion, we once again find that the scale is 1 centimeter equals 2 newtons. Excellent. Now we can measure the length of the resultant and use that scale to determine its magnitude. It looks like that resultant is about 7.5 centimeters long. So if we set up a similar proportion, we'll find that the resultant is 15 newtons. This lesson is about vector resolution. Let's say that we have a person pulling an 8-kilogram wagon with a force of 20 newtons at an angle of 30 degrees above the horizontal. What would the acceleration of the wagon be? Well, let's start with a free body diagram. We have the 8-kilogram wagon and a 20 newton force at an angle of 30 degrees above the horizontal. That dashed line just represents what horizontal would be. Newton's second law requires that the net force be in the same direction as the acceleration. Clearly this wagon is going to accelerate to the right. So the force that we would use to calculate the acceleration must also be to the right. But that 20 newtons is at an angle, so some of it is directed upward and some of it is directed to the right. We need to determine how much of it is rightward only. In this case, and in most cases, we care about the horizontal and vertical components. Let's draw and label them. Fx represents the component of the 20 newtons that is to the right, and Fy represents the component of the 20 newtons that is upward. How are we going to determine these? Trigonometry! I know that many of you are only taking trigonometry now, but I assure you the amount of trigonometry that we need to use to solve this problem is the basic trigonometry that you learned in middle school. Here's a reminder. Let's start with Fx. Since Fx is the adjacent side to the 30 degrees, and we know the value of the hypotenuse, let's use the cosine function. We know that the cosine of the angle is equal to the adjacent side divided by the hypotenuse. Let's plug in what we know. We know the angle is 30 degrees, and we know the hypotenuse is 20 newtons. We can cross-multiply to see that the horizontal component is the hypotenuse times the cosine of the angle. When we plug those into our calculators, we find the horizontal component to be 17.3 newtons. Now for the vertical component. Fy is the opposite side to that 30 degrees, so we use the sine function, where the sine of the angle theta equals the opposite side divided by the hypotenuse. We can substitute in the 30 degrees and the 20 newtons, cross-multiply, and find that the vertical component is equal to 10 newtons. Let's go back to our problem. Now that we know the horizontal component of the force is 17.3 newtons, we can calculate the acceleration of the wagon. So A equals F net over m. The net horizontal force is just the 17.3 newtons. We'll divide that by the 8-kilogram mass and find that the acceleration of this wagon is 2.16 meters per second squared. This unit is called motion in a plane. The first lesson of this unit is about horizontal projectiles. Projectile motion is when an object is projected, that is thrown or launched or something like that, near Earth's surface and travels in a curved path only under the influence of the force of gravity. The path of a projectile is described as being parabolic. This means like a parabola. The type of projectile motion that we're going to start with is horizontal projectiles. This is a case where an object is launched from a height in the direction that is parallel to the ground. This means that the initial vertical velocity is 0. At the very beginning, it's not heading upward at all, and it's not heading downward at all. So we're going to remember that VIY equals 0. Here's an example. Let's take a look at a problem like that in detail. Whatever speed the object is moving when it becomes a projectile is the initial horizontal velocity, or VIX. The projectile is launched from some height, which we'll call dy, right? That's vertical displacement, and it ends up with some horizontal displacement, which we call range. We have to remember that the initial vertical velocity, VIY, is equal to 0 meters per second. And we also have to remember that vertically, gravity is pulling down on the car. This means that AY, the vertical acceleration, is going to be 9.81 meters per second squared. Horizontally, once the car becomes a projectile, there are no forces pushing it forward or pulling it backwards. If there's no forces, that means there's no acceleration. So AX, the horizontal acceleration, is 0 meters per second squared. Let's say in this example problem that the car was originally traveling 30 meters per second and lands a distance of 100 meters away from the edge of the cliff. Let's try to figure out how tall the cliff is. As you can see, there's a lot of information here. We have all of the variables we're used to from uniform accelerated motion problems, but now they're duplicated. We have horizontal values for them, and we have vertical values for them. What's going to be really important for us is to have good organization. Rather than just making a list of givens, we're going to organize our information in a table, like this. You should definitely copy this table into your notes. Let's see where all the numbers from our problem fit. Well, first of all, since this is a horizontal projectile problem, we know 3 things. We know that the horizontal acceleration is 0, and the vertical acceleration is 9.81 meters per second squared. We also know that the initial vertical velocity is 0. Those 3 boxes will always be the same for every horizontal projectile problem. From this specific problem, we know that the initial horizontal velocity is 30 meters per second, and we know that the horizontal displacement, or the range, is 100 meters. You'll notice that the time row is not divided. That's because time is a scalar quantity. There's no such thing as vertical time or horizontal time, and that's actually really great for us. This means that if we have enough information in the x column, or we have enough information in the y column to calculate the time, we can then use that value for the time in the other column. In this specific problem, we have enough information in the x column. We know enough about the horizontal motion of this object to figure out how long it took to travel 100 meters horizontally if it was originally traveling at 30 meters per second and moved with an acceleration of 0. We're going to be using our UAM equations here. So we have d, vi, a, and we're looking for t, so we're going to use the equation d equals vit plus 1/2 at squared. You'll notice that I added in subscripts of x. You don't always have to do that, but my hope is that if we do include those, we will be sure to include only values from the x column when we substitute. So we have 100 meters equals 30 meters per second times the time plus 1/2 of 0 times t squared. If we solve that for t, we find that it took 3.3 seconds for that car to hit the ground. This means that it took 3.3 seconds to travel 100 meters horizontally, that it also took the car 3.3 seconds to travel its vertical displacement, which we'll calculate now. It turns out that we're going to use the same equation. You see this time I changed the x subscript to the y subscripts. Again, we want to make sure that we only use numbers from one column or the other. If we plug in our initial velocity and our time and our acceleration, we find that the vertical displacement is 53.4 meters. This is otherwise known as the height of the cliff. You try one. Let's say that we have a billiard ball that rolls horizontally off a 0.75 meter high table with a velocity of 12 meters per second. A picture of this would look something like that. I want you to figure out how far away from the table the ball would land. Here are some tips. First of all, and most importantly, organize your information in the table. Remember that you already know the vertical and horizontal accelerations and the initial vertical velocity. Finally, when you're doing your calculations, make sure that you only use numbers from the x column or the y column at a time. Let's take a look at the vertical velocity, the horizontal velocity, and the vertical acceleration at various points during a horizontal projectile's path. This first point is when it just leaves the table before it's had a chance to gain any vertical velocity. So it has some initial horizontal velocity, and now that it is in free fall, it has an acceleration, that is the acceleration due to gravity. A little while later, it still has the same horizontal velocity. There's nothing making it speed up or slow down, remember? And its vertical acceleration is still 9.81. At this point, however, it's had a chance to gain at least a little bit of vertical speed, so there's a little tiny vy. As we progress, you'll see that the horizontal velocity and the vertical acceleration remain constant, but the vertical velocity increases. As it travels, it gets faster and faster toward the ground. Once again, vx and ay are the same, but vy is bigger. Let's take a look at them all together. This lesson is about projectiles at an angle. Let's start right off with an example. Here's a football that is kicked with an initial velocity of 36 meters per second at an angle of 50 degrees above the horizontal. First of all, let's see that when it's kicked, it follows a parabolic path. Its horizontal displacement is called the range. Its maximum vertical displacement is called the height. It travels upward for some time, and then it travels downward for some time. And as long as the projectile returns to the same height where it was launched, the time up equals the time down. That is very important. The last important thing to note is that at the highest point, the vertical speed is 0. We've seen this before. It's not going up anymore. It hasn't quite started to come down. Its vertical velocity is 0. Let's take a closer look at that initial velocity. Like we did with horizontal projectiles, we're going to organize our information in the table. Where does this 36 meters per second go? Is it vix? Is it viy? What do we do with it? Well, it's not vertical and it's not horizontal, so it doesn't go in either of those boxes. We have to figure out the components of the initial velocity. The horizontal component, vix, and the vertical component, viy. Once we've calculated these, we can put them in the table. Therefore, vix will be vi cosine theta, and viy will be vi sine theta. Let's start actually filling out this chart. 36 meters per second times the cosine of 50 degrees is 23.1 meters per second, so we'll plug that in for vix. 36 meters per second times the sine of 50 degrees is 27.6 meters per second, so we'll plug that in for viy. Just like in horizontal projectiles, the horizontal acceleration is 0 because there's nothing pushing it forward or pulling it backward, and the vertical acceleration is 9.81 meters per second squared. This time we have to call it negative though. Since the initial vertical velocity is upward and the acceleration is downward, we can't let them have the same sign. Finally, we can note that the final vertical velocity is 0. Here's what we'll call each of the boxes that remain. dx is the range, dy is the height, ty is the time up, and tx is the total time. You'll see that this time we've split the t row. This isn't to say that there's a horizontal time and a vertical time, but there's a time that we care about for the vertical motion and a different time that we care about for the horizontal motion. You'll see how this works. Let's calculate the height. We have enough information in the y column to calculate how high the ball ends up going. You'll see here that I've added y to the subscripts. You don't have to do that. I'm just doing it to make it clear that we only want to pick numbers from the y column, not the x column. When we plug in our final velocity and our initial velocity and our acceleration, we can find that the height that this ball reaches is 38.8 meters. Now let's figure out how long it takes to get to the highest point. Right, this is the time up. Here's our UAM equation. We can plug in our final velocity and our initial velocity and our acceleration, and we'll find that it takes 2.8 seconds to get to the highest point. If it took 2.8 seconds to go up, then it also took 2.8 seconds to come down, which means overall it took 5.6 seconds from the time the ball was kicked to the time the ball landed. We're going to plug this in as Tx. Now let's figure out how far away the ball lands, the range. Once again, we'll use our UAM equation. You see this time that I have x in the subscript. We'll plug in our initial velocity, our acceleration, and our time, and we'll find that the range of this ball was 129.4 meters. Let's talk about that final horizontal velocity. Since there's zero horizontal acceleration, that means that the projectile doesn't speed up or slow down horizontally. This means that the final horizontal velocity is exactly the same as the initial horizontal velocity. So we can just plug in 23.1 meters per second there if we want to make sure that this table is totally complete. This lesson is about circular motion. We'll start with a review of acceleration. You don't have to write this part down. Acceleration is the rate of change of velocity. Here's an example. Let's say that the car accelerated from 0 meters per second to 30 meters per second over the course of 5 seconds. We could use the equation a equals delta v over t, plug in our final velocity and our initial velocity and our time, and find that the acceleration of this car was 6 meters per second squared. This would be considered a linear acceleration, that is, acceleration in a straight line, that is due to the change in the magnitude or amount of the velocity. Let's take a look at another example of acceleration. Here's a car that's going to travel around a circular track. It starts out traveling 15 meters per second north and ends up traveling 15 meters per second west after 2 seconds. Since velocity is a vector, 15 meters per second west is different than 15 meters per second north. Therefore, we can say that the velocity changed. Let's try to calculate the acceleration. A equals delta v over t. We plug in our initial and our final velocities and our time, and we get an acceleration of 0. But the velocity did change, so it was accelerating. The problem here is that the car is not accelerating because of a change of its magnitude of velocity. This is not an example of linear acceleration. This is an example of centripetal acceleration. We're still talking about the rate of change of velocity, but instead of the velocity changing because of a change in magnitude, it's changing because of a change in direction. This is specifically called centripetal acceleration, which is abbreviated with an A subscript C. Let's take a look at that example again. The car is traveling 15 meters per second, and the track has a radius of 30 meters. Now, whether this is a full circle or not doesn't matter. The part of the track that it's on is circular with a radius of 30 meters. Here's a new equation specifically for centripetal acceleration. AC equals v squared over r. We can substitute in the velocity of 15 meters per second and the radius of 30 meters, and we find that the centripetal acceleration is 7.5 meters per second squared. This is not telling us how quickly the car is speeding up or slowing down. The car isn't getting 7.5 meters per second faster each second. This number represents how quickly the car is changing direction. How quickly does this car get from heading north to heading west? Any acceleration is caused by a force. Centripetal acceleration is caused by centripetal force. Centripetal force is to centripetal acceleration, just as net force is to linear acceleration. You'll remember that net force is not one of the actual forces acting on the object. It's the result of all the forces that are acting on the object. Here are a few quick examples of net force. You don't have to write these down. Here's an object in free fall. It is experiencing a force of gravity only. That means that the net force is equal to Fg. A skydiver feels two forces, a gravitational force down and a drag force up from the parachute. In this case, we would say that the net force is the force of drag minus the force of gravity. Here's an object on a surface. If the surface is frictionless, or if the object is on wheels, we might only have an applied force, in which case the net force is equal to the applied force. If there is friction, it would probably be directed opposite of the applied force, so the net force would be the applied force minus the force of friction. My point here is that the net force is not one of the forces that you draw on your free body diagram. The centripetal force is the same way. The centripetal force is the result of one or more forces that could be labeled on a free body diagram. For a car driving around a curved track, the force that keeps the car in the circular path, in other words, the force that prevents the car from skidding off the road, is the force of friction. In this case, we would say the centripetal force equals the friction force. For the moon in orbit around the Earth, the force that keeps the moon traveling in a circle is the force of gravity. In this case, we would say that the centripetal force equals the gravitational force. In this final example, an athlete participates in a hammer throw. The force that keeps the mass traveling in a circle is the tension force in the rope. In this case, we would say that the centripetal force equals the force of tension. The equation for centripetal force will look very familiar. The centripetal force is equal to the mass times the centripetal acceleration. This is basically Newton's second law, where the force and acceleration are specifically centripetal. We've already learned that the equation for centripetal acceleration is AC equals v squared over r. It can be very convenient to combine these equations into one that relates the centripetal force to the velocity and the radius of the circular path. If we substitute in v squared over r for AC, we get Fc equals mv squared over r. Let's give this a shot. If the car in our previous example had a mass of 1,600 kilograms, we could figure out the centripetal force acting on the car. Fc equals mv squared over r. and we can substitute in our mass and velocity and radius to find that the centripetal force acting on this car is 12,000 newtons. It's very important for us to be able to answer this question as well. What force is providing the centripetal force in this situation? That is, what force that we could draw on a free body diagram is keeping this car traveling in a circular path? In this case, it's friction. Before we're done, let's take a look at the direction of some very important vectors. Centripetal is a word with Latin roots that means center seeking. That means that anything that is described as being centripetal should point toward the center. So centripetal force is a force vector that points toward the center of the circle, and centripetal acceleration is an acceleration vector that points toward the center of the circle. The velocity is a different story. The velocity of an object traveling in a circle is described as tangential, meaning like a tangent. If you don't remember, a tangent is a line that touches a circle at just one point. At this moment, the velocity of the car is in this direction. This unit is about momentum, energy, work, and power. This lesson is about momentum and impulse. Momentum is considered the quantity of motion and is defined as the product of an object's mass and velocity. Momentum is a vector quantity. So momentum is mass times velocity, and if we write this out like a normal equation, we will write P equals mv. That's right, P stands for momentum. Nobody knows why. M is mass, V is velocity. Let's take a look at the units for momentum. Mass, we always measure in kilograms. Velocity, we always measure in meters per second. So if we take an amount of kilograms and multiply it by an amount of meters per second, we end up with kilogram meters per second. There's no special unit for this. We just say kilogram meters per second, and we write kgm over s. Here's an example of a simple momentum problem. What is the momentum of a 65 kilogram student running with a velocity of 4.5 meters per second? Well, P equals mv. Plug in the mass and the velocity. We find that the momentum of this student is 292.5 kilogram meters per second. Now I want to introduce this other term, impulse. You guys remember Newton? A equals F net over m? Remember when we did kinematics? A was delta V over T? Both of those things equal A. Therefore, both of those things equal each other. And if we cross multiply, we'll get F net T equals m delta V. And both of these terms are very important. M delta V can also be called delta P, the change of momentum. If an object changes velocity, it will have more or less momentum than it used to have. And F net T is defined as impulse. That's right, capital J is impulse. Why? Nobody knows. Let's take a look at the units for impulse. F net, any force, is measured in newtons. Time is measured in seconds. And so if we plug in newtons and seconds, we get newton seconds. Let's take a closer look. A newton, if you remember, is a kilogram meter per second squared. If we multiply this by a second, one of the seconds in the denominator cancels, and we're left with kilogram meters per second, which is what we should expect. If impulse is equal to change in momentum, then the impulse units, newton seconds, should be the same thing as the momentum units, kilogram meter per second, and that's exactly what we see here. Let's take a look at an example of an impulse problem. How much impulse is being applied to a baseball when it is struck by a bat if the bat exerts a force of 37,000 newtons on the ball and they are in contact for only 2/1000ths of a second? Here we go. J equals F net T. Plug in the 37,000 newtons and the 0.002 seconds, and we'll find that the impulse applied to the baseball was 74 newton seconds. Now it's time for the make your own Sunday bar. Actually, make your own equation bar. Here we have four terms that are all equal to each other. This, however, is not an equation. An equation has one equal sign and a term on either side. So what we're going to do is pick two of these to create an equation. The first step will be to make a list of givens. The next step will be to select two of those terms based on our givens and our unknown. We'll set those terms equal to each other, and we'll solve. Let's take a look at an impulse momentum problem where we have to use the make your own equation bar. A car's momentum increases by 5,000 kilogram meters per second in 2.5 seconds. How much force must have been applied to the car during that time? So first we'll start with our list of givens. We know that the change in momentum is 5,000 kilogram meters per second. We know that the time it takes is 2.5 seconds, and we know that we're looking for the force. Now we can make our equation. Since we're looking for the force, we should definitely use the F net T term as one of our two choices. Since we're given the change in momentum, we should make that our second choice. This means we'll write the equation delta P equals F net T. Now we can substitute in what we know and solve. 5,000 kilogram meters per second equals F net times 2.5 seconds, and we find that the net force is 2,000 newtons. This lesson is about conservation of momentum. The law of conservation of momentum states that the total momentum of a closed system remains constant. A system is just a fancy word for a group of objects and their interactions. And a closed system is a system to which no energy is added or removed. On the reference table, they remind you of the law of conservation of momentum by telling you P before equals P after. That is, momentum before some event is equal to the momentum after that event. Here's an example of a problem that involves the conservation of momentum. Here we have a purple ball of mass 0.4 kilograms traveling 12 meters per second toward a blue ball that is 0.3 kilograms, traveling only 10 meters per second. Since the purple ball is traveling faster, it's eventually going to collide with the blue ball. And afterward, they'll both be moving in the same direction, but their velocities are going to be different. Because of the collision, the purple ball slows down to only 9.5 meters per second. What we want to figure out is how fast is the blue ball moving after the collision. Let's try to solve this methodically and look at one part of this problem at a time. Let's start with the before side. Beforehand, the momentum of the system is just the sum of the momentum of each ball. We'll call them 1 and 2. So beforehand, we have a total momentum that is the same as the momentum of the purple ball plus the momentum of the blue ball, P1 plus P2. We could take an extra step here and write out the equation for the momentum of the purple ball and the momentum of the blue ball. It's just each one's mass times its velocity. And we can plug these numbers in. We know them. 0.4 kilograms at 12 meters per second plus 0.3 kilograms at 10 meters per second. And we find that before the collision, this system has a total momentum of 7.8 kilogram meters per second. Now, let's look at after the collision. And we'll start at the same place. After the collision, the total momentum is the sum of the momentum of the purple ball and the blue ball, again, P1, P2. And as good practice, we'll write out the equations, m times v for each of them. Now, before we plug things in, let's remember the law of conservation of momentum. P before equals P after. So we can plug in a value for P after. It's just going to be the same as P before, 7.8 kilogram meters per second. Then we can also plug in masses that we know and the velocity of the purple ball, which was a given. If we solve for V2, we find that the blue ball, after the collision, is traveling 13.3 meters per second. If we look at the big picture here, we can see that the momentum of each ball is different than it was before the collision. The purple ball lost some momentum, and the blue ball gained some momentum. The law of conservation of momentum tells us that the total momentum of the system has to be the same. There are two main types of problems that we'll be working with that involve the law of conservation of momentum. The first type are called inelastic collisions. This is when two objects collide, like in the previous example, only here they stick together, and subsequently they move as one object. The other type of problem is what I call an explosion, and this doesn't have to have a loud bang. This is simply when two objects start out together at rest, and then for some reason they move apart from each other. Let's start with inelastic collisions. Here we have a lump of clay traveling with some velocity toward a block that's at rest on a surface, and when it collides, it's going to stick to it. And then the lump of clay and the block are going to move together to the right at some velocity. Before we plug in any numbers, let's take a look at how the law of conservation of momentum affects this particular problem. We start out with our reminder from the reference table that P before equals P after. The momentum of the flying blob of clay plus the momentum of the block at rest is going to be equal to the momentum of the block and blob of clay that are stuck together moving afterward. Like we did before, let's write out the equation for momentum for each side. Only now, instead of doing it as just the before side and then as the after side, we're going to kind of do it all together. You'll see. So here's what I would write. I would say that beforehand, there's a momentum of the clay. We'll call that 1, M1, V1. And there's the momentum of the block, M2, V2. Afterward, they move as one object. So rather than write two m times v terms, instead, let's acknowledge that this one object is moving together at the same speed, and the mass of this object is the sum of the two masses. So afterward, we have just one object with a mass of m1 plus m2 moving at some final speed. This might make more sense in a minute when I show you some numbers and we substitute. Before we do that, though, let's take a look at what's going on beforehand. That block is at rest. Its velocity is 0. That means m2 v2, whatever the mass is, times 0, is 0. And that's almost always going to be the case when we look at inelastic collisions. A moving object is going to collide with a stationary object, and then those two objects are going to move off together at some speed. This is going to be our general equation for inelastic collisions. Now let's make up some numbers. Let's say the blob of clay is 1.2 kilograms, moving at 16 meters per second, colliding with the block that is at rest and has a mass of 9 kilograms. Afterward, the mass of the kind of one object is 1.2 kilograms plus 9 kilograms, and we want to figure out how fast would this be moving. So we can take all those numbers and we can plug them into the equation. We'll see that we only have one variable, and we'll solve for it. Beforehand, all we have is the momentum of the clay, 1.2 kilograms times 16 meters per second. And afterward, we have the one object that has a mass of 1.2 kilograms plus 9 kilograms, moving at some speed vf, and that's what we're looking for. So do a little algebra, 9.2 kilogram meters per second equals 10.2 kilograms times vf. And then we can find that this clay block system is moving at 1.9 meters per second after the collision. Once again, let's take a look at the big picture. Afterward, there's a lot more mass moving, but the law of conservation of momentum tells us that the total momentum has to be the same as before. So if we have a lot more mass moving after they collide and stick together, then that object must be moving at a much slower speed, and that's exactly what we see. Let's go back to our definitions of these types of problems and write this equation, plain as day, where we will remember it and be able to refer to it. m1v1 plus 0, and I like that 0 to remind us that there's an object there, but it is at rest, equals the sum of m1 plus m2 times the final speed. Now let's move on to explosions. Here we have a cannon and a cannonball that are both at rest. The cannon is just sitting at rest on the ground, and the cannonball is just sitting at rest on the inside. Now we're going to light the fuse and fire the cannonball. As you can see, the cannonball has some velocity to the right, and the cannon has some what we call recoil velocity to the left. And we can use the law of conservation of momentum to figure out that recoil velocity. But again, let's first use the law of conservation of momentum to write a general equation for this type of problem. Like before, we'll start with the basic statement that the total momentum before is equal to the total momentum after. And in this case, we have two separate objects before and after. At no point are they in a situation where they're stuck together and would have to move together. What's convenient in this type of problem is that before the explosion, everything is at rest. The cannon is at rest on the ground, and the cannonball is at rest inside the cannon. After we see that the two objects are moving in opposite directions, we can't call both of those directions positive, so we're going to choose to call the direction that the cannonball is moving negative. If we put these together, we're going to find the following equation. Beforehand, there is zero momentum, and afterward, we have the momentum of each object adding together, but the momentum of one of the objects is going to be negative. If we rearrange this equation a little bit, we get the very straightforward equation m1v1 equals m2v2. The momentum of the cannon after the explosion is the same as the momentum of the cannonball, and they happen to be in opposite directions. This is a very important equation. Now, let's make up some numbers for this problem and actually solve for the recoil velocity of the cannon. Let's say that the cannon has a mass of 250 kilograms, the cannonball has a mass of 15 kilograms, and after the explosion, the cannonball is moving 50 meters per second. What's the final velocity of the cannon? All we have to do is plug those numbers in. 250 kilograms times v1 equals 15 kilograms times 50 meters per second. And when we do some algebra, we find that the velocity of the cannon is 0.33 meters per second. That's what we call the recoil velocity. Just like before, let's go back to our definitions page and write that equation for explosions. m1v1 equals m2v2. This lesson is about energy. There are many, many different types of energy. There are two specifically that we'll be dealing with right now. The first is kinetic energy. Kinetic energy is energy of motion. Moving things have this particular type of energy. The equation for kinetic energy is Ke equals 1/2 mv squared, where Ke stands for kinetic energy, m is mass, and v is velocity. Let's take a look at the units. If we take a kilogram and we multiply it by the square of a meter per second, we end up with kilogram meter squared per second squared. This looks similar to some other units we've seen this year, but it's different. We have a special name for this unit. It's called a joule. Here's an example of a kinetic energy problem. What is the kinetic energy of a 1,350 kilogram car traveling 28 meters per second? As always, we'll start with the equation. We can substitute in our mass and velocity. And when we solve, remembering, of course, to square the 28 meters per second, we find that the car has a kinetic energy of 529,200 joules. The other type of energy we'll be learning about is potential energy, specifically gravitational potential energy. This is energy something has because of its position above the ground. The equation for potential energy is the weight of an object times the height of an object. This can also be written as mgh, the mass times the acceleration due to gravity times the height. Once again, let's take a look at the units. If we look at the equation mgh, we'll see that we would substitute in kilograms, meters per second squared, and meters. When we multiply all three, we end up with kilogram meter squared per second squared, which we have previously learned is a joule. Instead, if we look at the equation Fg times h, we see we would substitute in newtons times meters, and if you think back to September or October, you know that a newton is a kilogram meter per second squared. When we multiply that by a meter, as we would expect, we end up with kilogram meter squared per second squared. Every form of energy that we'll learn about is measured in joules. Let's take a look at an example of a potential energy problem. How high would one have to lift a 95 Newton object in order to give it 684 joules of potential energy? We'll start with the equation, Pe equals Fgh. I've selected this form of the potential energy equation because I know the weight of the object, 95 newtons. I don't know the mass of the object. When I substitute in the energy and the weight, I can find that the height is 7.2 meters. This lesson is about work and power. We've previously talked about two types of energy, kinetic and potential, but we never talked about where that energy comes from. An object has kinetic energy because it's moving, but where do they get it? The answer is work. An object has energy because someone or something does work on it. When you do work on an object, you lose energy. You get tired, you have to eat something. When work is done on you, you gain energy. Work is being done on you when you are on an escalator or in an elevator. Let's take a look at an example. Here we have a mass attached to a rope that's hung over a pulley. This person is going to pull down on the rope, lifting the mass into the air. The person lost energy. They are tired. They have to go have a snack. The mass gained energy. Right here, it specifically gained gravitational potential energy. So clearly, work is related to energy. In fact, work equals the change of energy. We can write that as W equals delta E. One way that we can calculate the work is to find the product of the force that's being exerted on an object and the displacement of the object. And it's really important that the force and the displacement have to be in the same direction. So let's say if there's an upward force on an object, but the object is moving horizontally, that upward force is clearly not responsible for the horizontal motion. The other equation we can write for work is that work equals force times displacement. Let's take a look at that example again. So this person exerts a downward force of 25 newtons on the rope, which, through the pulley, exerts a 25 newton force up on the mass. And if the mass has a displacement of 0.8 meters, we can find out how much work was done. So work is force times displacement. 25 newtons times 0.8 meters gives us work of 20 newton meters. And I think we've seen before that a newton times a meter is the same thing as a joule. So this person did 20 joules of work lifting the mass. A common phrase that you'll see is work done against, and then they'll name a force that you've learned about before. And I want to give you an idea of what this means so that you're not confused. So in this example that we've been looking at, work is being done to overcome the force of gravity. We're trying to lift this mass opposite the direction that gravity acts, and so this would be called work done against gravity. In a different example, right, this person is trying to move this box, and the reason it's difficult is because of friction. So in this case, the person is doing work to overcome the force of friction, and so this would be called the work done against friction. We'll talk about that more a little later, but I wanted to introduce you to this phrase. This brings us to power. Power can be defined as the rate at which work is done. Now I'm going to show some equation, but you don't have to write anything down until we have a big equation in box. So we could write this simply as power equals work divided by time. But we've already seen that work is equal to force times displacement, so we could rewrite this as power equals force times displacement over time. And if you think back, way back to the beginning of September, we know that d over t is the equation for average velocity. So we could replace d over t in the equation with v bar, which would give us power equals force times average velocity. And so we can put all of these together. That's what you should write down. Power can be work over time, it can be force times displacement over time, or it can be force times average velocity. Let's take a look at an example of a power problem. And why not go back to that original example? So this person is lifting the mass 0.8 meters by exerting a force of 25 newtons, and let's say that this person does this in 15 seconds. We want to know what power the person has while lifting. Based on the givens that we can see here right on the screen, we know force and displacement and time, so let's use the power equation, power equals force times displacement over time. We can plug in the 25 newtons, the 0.8 meter, and the 15 seconds, and we can find that the power is 1.3 newton meters per second, which we know is joules per second. So we have a power of 1.3 joules per second. For some reason, scientists decided that joules per second should have a special name. So this unit, joule per second, we're going to call a watt. And you've definitely heard of watts before. Light bulbs are measured in watts. 60 watts means that light bulb uses 60 joules of energy every second. So finally, we'll say that the power of this person was 1.3 watts. This lesson is about conservation of energy. Conservation of energy is the idea that the total mechanical energy of a system remains constant. Energy doesn't appear out of nowhere, and energy doesn't disappear into nowhere. One form of energy can transform into another type, but the total amount of it always stays the same. Let's take a look at an easy example. Here's an object some distance above the ground, and in this position, it has a certain amount of potential energy. If we let go of it and it falls, as it falls, it's going to lose potential energy because its height is less. And as it loses potential energy, it's going to start gaining kinetic energy. The total amount of energy that this object has is the same every step of the way, but as it falls, the potential energy is transformed into the kinetic energy. First, we'll take a look at conservation of energy without including friction. It'll be a little bit easier this way. So, without friction, we can say that the total mechanical energy of an object equals the sum of the potential energy and the kinetic energy. We can write this as ET equals PE plus KE. And remember, the total energy always remains constant. Let's take a look at a bigger example. This cannon is going to fire a cannonball straight up into the air. The cannonball has a mass of 7 kilograms, and when it leaves the cannon, it's traveling with a velocity of 42 meters per second. Up top, the cannonball is shown at its highest position. What I'd like us to figure out is the height that the cannonball reaches. Since we really don't know anything about the cannonball up at its highest point, let's focus on the location where we do know information about the cannonball. That's the bottom, right after it leaves the cannon. Let's write out the equation for the total energy of the cannonball just after it leaves the cannon. So we have ET equals PE plus KE. Well, the cannonball hasn't really risen yet. Let's say that the potential energy is 0. The kinetic energy would then be 1/2 mv squared. If we substitute in the 7 kilograms and the 42 meters per second, we find that the total energy of this cannonball is 6,174 joules. Okay, great, you might be thinking, but we weren't looking for the total energy of the cannonball, we're looking for the height of the cannonball. Well, you know what? Hold your horses. If we know the total energy of the cannonball right after it's fired, then we know the total energy of the cannonball when it gets to its highest point. It's the same. That's conservation of energy. The total energy of the cannonball remains constant. If it was 6,174 joules when it was fired, it's always going to be 6,174 joules. In the beginning, all of that energy was in the form of kinetic. Well, how much kinetic energy do we have now? I hope you remember that at the highest point, the velocity is 0. This means we have no kinetic energy. Okay, how much potential energy do we have? Well, we don't know. Let's take a look at the equation for total energy. If we have 6,174 joules of total energy, and we have 0 kinetic energy, then all of the energy is in the form of potential. Now we can go ahead and calculate the height. If we know the potential energy is 6,174 joules, and the equation for potential energy is mgh, we can substitute in our energy, mass, and the acceleration due to gravity, and figure out that the height of this cannonball is 89.9 meters. This is just one of many different examples we could have looked at, and of course we'll practice a lot more of them in class. Now let's look at what happens when we include friction in our conservation of energy situations. So let's start by making it clear, total mechanical energy is still going to be conserved. That is a law of nature. But now some of the energy is going to transform into heat. We're going to call this internal energy. This is energy that is contained in the molecules of the object. We can now write out the same equation for total energy that you'll find on your reference table. ET equals PE plus KE plus Q. Q stands for internal energy. When work is done against friction, internal energy is produced. Here's that phrase, work done against friction, that we've seen before. Now let's take a look at a conservation of energy example with friction. Here we have a 5 kilogram mass at rest on a 3 meter tall incline. When we release it, it slides down to the bottom, reaching a final velocity of 6.2 meters per second. The question we want to answer is how much work is done against friction. When you see that phrase, you want to be thinking internal energy. This is our way of asking for how much internal energy is produced during this process. As we've done before, let's start at the beginning and figure out how much total energy this object had. So this is the sum of its potential, kinetic, and internal energy. Well, at the top it's at rest, so there's no kinetic energy, and since it hasn't moved yet, there hasn't been any friction, so there hasn't been a chance to produce any internal energy. At the top, there's only gravitational potential energy. If we substitute in the mass and the acceleration due to gravity and the height, we can find that this object at the beginning had a total energy of 147.15 joules. Now we can take a look at what's happening to this object at the bottom. Once again, we can start with our equation for total energy, PE plus KE plus Q. At the bottom, the object doesn't have any height anymore, and therefore the potential energy is zero. The kinetic energy can be calculated using the equation 1F mv², and we have our Q term, our internal energy. That's what we're looking for. We can substitute in what we know. We know that this object is still going to have a total energy of 147.15 joules. We can substitute in the mass and the velocity. Whoops, that should be squared. And we can find that at the bottom, the kinetic energy is 96.1 joules. So this object started out with a little more than 147 joules of potential energy, but now at the bottom it only has about 96 joules of kinetic energy. If we didn't know any better, it would seem as if some energy had been lost. But we know that friction produces heat, and so we can figure out that this process produced 51 joules of internal energy. This is the work done against friction. This is the amount of energy turned into heat during the process. This lesson is about wave characteristics. There are many different types of waves. We have water waves, sound waves, light waves. People make waves at a sporting event, and even zombies come in waves. But as far as we're concerned, a wave is a continual disturbance, oscillation, or vibration that transfers energy from one location to another. An oscillation is a regular variation in magnitude or position. So this is something moving up and down over and over again, or left and right over and over again, or something like that. This is very important to note. A wave transfers energy without transferring mass. If you have only a single oscillation, we call that a pulse. There are two main types of waves. The first is called mechanical waves. This is a wave that travels as an oscillation of a medium. Examples of mechanical waves are water and sound. Water waves are the oscillation of water molecules, and sound waves are the oscillation of air molecules. Mechanical waves cannot travel through a vacuum because they require something physical to be there oscillating in order for the energy to transfer. The other type of wave is electromagnetic waves. These consist of electric and magnetic fields, and an example of this is light. We'll come back to electromagnetic waves in a few lessons. Looking only at mechanical waves, there are two other categories of wave. The first is a transverse wave. This is a wave in which the particles of the medium oscillate perpendicular to the motion of the wave. Here's a simple diagram that you could copy into your notes that shows us basically what a transverse wave looks like.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
The other type of mechanical wave is a longitudinal wave. This is a wave in which the particles of the medium oscillate parallel to the motion of a wave. This diagram is a little bit more complicated. This is basically the coils of like a slinky, and you can see in some places the coils are bunched up really close, and in some places the coils of the slinky are spread out a little bit more. Try to copy something like that into your notes. It will be important for you to know that sound waves are longitudinal.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
The focus of this lesson is to learn about the different characteristics of waves. We'll mostly be looking at transverse waves, but these characteristics apply to both transverse and longitudinal. Here's a quick list of the characteristics we'll be looking at. Wavelength, which is abbreviated by the Greek letter lambda, kind of looks like an upside down lowercase y. Amplitude, frequency, period, which is a capital T, as opposed to the lowercase t that we use for time, and speed. Now we'll take a look at each one of those individually. Before we go any further, let's introduce a couple of terms that will help us describe the different parts of a transverse wave. The peaks of a transverse wave we'll call crests, like the crest of a hill. The valleys of a transverse wave we'll call troughs, kind of like the thing a pig eats out of a trough. So with that terminology in mind, we can say that the wavelength of a wave is the distance between consecutive corresponding points. Wavelength, being a length, is measured in meters. So corresponding points are 2 points that match. They're identical points on neighboring oscillations in the wave. Right? That's what consecutive means, one right after another, so neighboring. There are literally an infinite number of places we could label or measure the wavelength. There are a few that kind of make the most sense. So here's one example. This is from the beginning of a crest on one oscillation to the beginning of the next crest. Another logical place to label or measure the wavelength is from the top of one crest to the top of the next crest. Those points are obviously corresponding to each other, they match, right? And there's no other crest in between. Likewise, we can measure from one trough to another trough, and really we can measure between any points that meet those criteria. So here's just a random one. So 3/4 of a way through a trough to the next point that is 3/4 of a way through a trough. Amplitude is basically the height of a wave, but we have to measure very specifically. It's the distance from the middle of the wave, that dotted line, to the top of a crest or to the bottom of a trough. This means that we can measure the amplitude here, or we can measure the amplitude here. Really, the only other thing that you'll need to know about amplitude is that the energy of a mechanical wave is directly proportional to its amplitude. Okay, how about frequency? A really broad way we could define frequency is the number of occurrences of a repeating event per unit time. but don't write that. For us, we'll describe frequency as the number of complete wavelengths produced per second, or the number of oscillations per second. There's no equation for this on the reference table, but we could sort of write it in the form of an equation like this. F for frequency is equal to the number of wavelengths that you see in a picture or that are described to you. That's number of complete wavelengths, or number of oscillations, or number of crest-trough pairs, however you want to think about it, divided by time. We have a new unit that goes along with frequency. It's called Hertz. Now the abbreviation is capital H lowercase z, and H isn't a prefix. Hz is the abbreviation for Hertz. And it basically means cycles per second. Let's take a look at an example of a problem involving frequency. So here's Frank, and he's making waves on a rope by moving his arm up and down, which he does 20 times in 10 seconds. So in 10 seconds, he moves his arms up and down, that's an oscillation, 20 times. So we want to figure out what are the frequency of the waves that he's making. So frequency is the number of wavelengths that are created divided by time, and we can see from the description that he's creating 20 wavelengths, that's 20 oscillations, every 10 seconds. So we have 20 divided by 10 seconds. Notice the 20 doesn't have any units. We don't measure that, it's just we counted. We counted to 20. 20 divided by 10 seconds gives us a frequency of 2 oscillations per second is a way we can describe that. And if we want to put our new unit on there, which we do, we can call that 2 hertz. Let's take a look at period. Again, the very general definition we can write for period is that it's the interval of time between successive occurrences of a cyclic phenomenon. But again, don't write that. For us, period is the time for one complete wavelength to be produced. In other words, this is the time for one complete oscillation. Just like we did for frequency, we're going to write this in sort of an equation form. Like what we wrote for frequency, this is not in the reference table, but this is a really convenient way to think about period. So you take all the time that has passed while the waves were created and divide it by the number of wavelengths that were produced, or again, the number of oscillations. The unit for period is just second. Let's take a look at an example. So Kelly is floating on an inner tube in the ocean, and she notices that she bobs up and down 6 times every minute. So each time she bobs up and down, that's one complete oscillation, that's one wavelength. So we can figure out the period of the ocean waves that she's floating on if we do a little bit of math. So period is the total time that has passed divided by the number of wavelengths or oscillations produced within that time. So the time that she measured was 1 minute, so 60 seconds, divided by the 6 complete oscillations that she observed gives us a period of 10 seconds. So she bobbed up and down in 10 seconds, and then bobbed up and down again in another 10 seconds, and so on and so forth. Frequency and period have a unique and important relationship. Take a look at the equations you just wrote for them. Do you notice that the equation for period is just the equation for frequency flipped upside down? Or I guess you can say it the other way around. This is because frequency and period are reciprocals of each other. This means that we can write a very simple equation that relates frequency and period. We can write it either as f equals 1 over t, or as t equals 1 over f. And finally, let's talk about the speed of waves. The speed of a wave means exactly the same thing as the speed of a car, or the speed of a person, or the speed of anything. It represents how quickly a wave can get from one place to another. What we're going to do here is figure out an equation for the speed of a wave based not on how far it travels and how much time that takes, but the fundamental properties of the wave itself. Watch. So let's start with something we already know. V equals d over t. Speed equals distance over time. Now let's think about the new stuff that we learned. Right? The characteristic of a wave that's measured in meters, like distance, is wavelength. And the characteristic of a wave that's measured in seconds, like time, is period. So let's rewrite that equation that we've known since September as v equals lambda over t. That is, the speed of a wave equals the wavelength of the wave divided by the period of the wave. Now remember, we just learned that period and frequency are reciprocals. This means that we could also write the equation for the speed of a wave as v equals f lambda, and that's actually the way that it's presented on your reference table. Let's take a look at a couple examples using the new wave speed equation. So we want to know what's the speed of a water wave that has a wavelength of 8 meters and a period of 4 seconds. Well, it's pretty straightforward. V equals lambda over t. Now we wrote this equation because we know the period of the wave, not the frequency. We can plug in our 8 meters and our 4 seconds, and we can find out that the speed of this wave is 2 meters per second. Notice, we didn't have to know how far the wave ultimately travels, or how long it takes to get to its destination. All we had to know were those two fundamental characteristics of the wave itself, its wavelength and its period. Alright, let's take a look at another example. What is the wavelength of a sound wave with a speed of 331 meters per second and a frequency of 500 hertz? Now this time, since we know the frequency, we'll write the wave speed equation that has frequency in it, v equals f lambda. And we can plug in our speed and our frequency, and when we divide both sides by 500, we can find out that the wavelength of this wave is 0.662 meters. This lesson is about the superposition of waves. Superposition of waves means that there are two waves in the same place at the same time. They're overlapping, like the pink wave and the blue wave here. In this lesson, we'll talk about a few phenomena that occur when two waves are superimposed. The first phenomenon is known as interference. When two waves are superimposed, they'll interfere with each other. This means that the magnitudes of the displacements of the waves combine to form the resultant wave. Take a look at this simple example. We have this red pulse moving toward the right, and we have this blue pulse moving toward the left. Eventually, they get to the same place at the same time. Now, assuming this is a mechanical wave, the particles of the medium can't be in two places at the same time. So the displacement of the red pulse and the blue pulse combine to give us the resulting wave. If we call the displacement of the red pulse 1 and the displacement of the blue pulse 2, then the resulting wave while they're superimposed would be 3. Now after they interfere with each other, they just continue going the way they were going as if nothing ever happened. Let's take a look at a couple of real-life examples of this. Here we have two pulses heading toward each other, and right there, they interfere with each other to cause a taller pulse. Same thing here, two pulses with positive displacement heading toward each other, and when they get to the same place at the same time, they will interfere with each other, combining their displacements to create one large pulse, and then they continue on their way. There's a slightly different way that interference can happen as well. Let's take a look at this. Here's a red pulse moving toward the right again, and a blue pulse moving toward the left. And now when they get together, their displacements are in opposite directions. We still need to combine those displacements to figure out what the resulting wave will look like. So in this case, we can kind of think of the red pulse as having a displacement of like -1, and the blue pulse as having a displacement of +2, and you put those together, you get +1. So these two pulses kind of cancel each other out a little bit. Like we saw before though, when they're done interfering, they continue moving in the direction they were originally moving, with the displacements they originally had, as if nothing ever happened. Let's take a look at a couple of real-life examples of this. The trough on the left and the crest on the right have just about the same displacement, so when they interfere, you should expect the resultant displacement to be 0. You can see that right here. We've just observed both types of interference. The first type was called constructive interference. This is when the interfering waves have displacement in the same direction. You can see in this diagram that wave 1 and wave 2 have displacement in the same direction right here. This results in constructive interference. Think of constructive as like building something bigger and bigger. The other type of interference that we saw was destructive interference, and this is when interfering waves have displacement in opposite directions. Take a look over here. Wave 1 has displacement above the midline, wave 2 has displacement below the midline, and you can see down there, where they're in superposition, that they basically cancel each other out. Let's take a look at two final examples. Here's constructive interference. And here's destructive interference. One way that we can explain whether two waves will constructively or destructively interfere is by talking about their phase difference. This is the difference in degrees of two waves of equal frequency and wavelength. Let's take a look at the sine function and use this as a reference. I use this because hopefully it's something that you're familiar with. So the sine curve kind of looks like a transverse wave. It has a crest and a trough. The crest of a sine wave happens at 90 degrees, and the trough of a sine wave happens at 270 degrees. And we're going to use these two numbers to help us understand phase difference. So here are two waves, and if I put them literally on top of each other, you won't be able to see that there are two. So imagine that these two waves are superimposed. They're in the exact same place at the exact same time. So just like we said a few seconds ago, crests are 90 degrees, troughs are 270 degrees. Same thing for the yellow wave. And if we look at how these line up, we'll see that the crests line up with the crests, and the troughs line up with the troughs, and so we would say that there's a phase difference of 0 degrees. 90 minus 90 is 0, 270 minus 270 is 0. The result of a 0 degree phase difference is maximum constructive interference. Here are those two waves again, but I've shifted them. We're going to use the same numbers though. Crests are 90 degrees, troughs are 270 degrees. If we imagine that these two waves were superimposed in the same place at the same time, we would see that troughs and crests line up this time. And so 270 minus 90 is 180. And 90 minus 270, well, it's negative 180, but it's still 180 degrees apart. And so a phase difference of 180 degrees is going to result in maximum destructive interference. There are a couple phenomena I want to introduce that can happen when two waves interfere with each other. The first is called a standing wave. This is a pattern of crest and troughs in a medium that appears to remain in one place. This is sometimes described as a stationary wave. And this occurs when two waves of identical wavelength, amplitude, and frequency are traveling in opposite directions through a medium and have become superimposed. Take a look at this animation. The red wave and the blue wave are the two identical waves. The blue wave is traveling to the right, the red wave is traveling to the left. The black wave is the standing wave. You can see there are certain points on that wave, those red dots, where maximum destructive interference is always happening. It doesn't matter what parts of the red wave and the blue wave are at those points, they always completely destructively interfere with each other. We call these places nodes. In between the nodes, the waves are experiencing varying degrees of constructive interference. Unlike the nodes, which are always maximum destructive interference, you can see that the red and blue wave fluctuate from maximum positive constructive interference to maximum negative constructive interference. This is what causes the pattern of crests and troughs. So when the red and blue wave are crests, you get a crest. When they're troughs, you get a trough. These areas in between the nodes are called antinodes. If you like making music or listening to music, standing waves are super important. When you disturb the string of a guitar or a ukulele or a violin or a cello or your vocal cords, a standing wave is created. When you blow air into a clarinet or a flute or a saxophone or a tuba or a trombone or whatever, a standing wave is created inside that instrument. When you strike the surface of a percussion instrument, a standing wave is created inside the material of that instrument. Whatever you do to play your instrument, the whole point is to change the frequency of the standing wave created to get different pitches. pitch and frequency are the same exact thing. We can talk more about that in class. The other phenomenon that occurs, and this also relates to music, is called beats. Beats are the alternating loudness and softness of a sound wave due to the interference that's happening. Here's an example. The loud part is caused by constructive interference, and the soft part, the quiet part, is caused by destructive interference. Here's a visual example. This green wave and this pink wave look pretty similar, but if we overlap them, we can see that their wavelengths, their frequencies, are slightly different. At these places, the two waves would interfere constructively, causing the louder part of the sound. At these places, the waves would interfere destructively, causing the quieter part of the sound. There's a very simple equation that goes along with beats, and that is the equation to figure out the beat frequency, how many times per second the sound fluctuates from loud to quiet. And here it is, the frequency of the beat is simply the absolute value of the difference between the frequency of the two waves. So for instance, if we had one wave that had a frequency of 220 Hz, and another wave that had a frequency of 223 Hz, the frequency of the beat would be 3 Hz. That means 3 times every second we would hear the sound fluctuate between loud and quiet. Listen. That audio clip was 5 seconds long. If the beat frequency is 3 Hz, how many times should you hear the sound fluctuate from loud to quiet? Go back and listen again. Let's look at another example. We'll start with the same 220 Hz frequency, but now we'll combine that with the 240 Hz frequency. This means that the beat frequency is going to be 20 Hz. 20 times every second, it should fluctuate between loud and quiet. This is going to be hard to hear, and probably impossible to count. I think you can still tell that it's fluctuating between loud and quiet. One final example. Again, the 220 Hz. Now let's combine that with 440 Hz. For the musicians out there, these two frequencies are an octave apart. When you double the frequency, you go up an octave. Anyway, the beat frequency here would be 220 Hz. This probably won't sound like a fluctuation between loud and quiet. It'll kind of just sound like one continuous noise. This lesson is about wave phenomena. First, let's talk about the motion of particles in a medium. It's important to remember that waves transfer energy without transferring mass. It could also be noted that the particles on a transverse wave move only up and down, and the particles in a longitudinal wave move only right and left. Let's take a look at an example. Here's a boat floating on top of water waves. The wave moves from left to right, and as the wave passes, the boat simply bobs up and down. I want to try to explain this a little bit further. So here we have two oscillations of a wave. The wave is traveling to the right. In the front of the wave, we have a trough, and at the end of the wave, we have a crest. This wave will always look just like that. It's just going to shift to the right as it moves. Let's take a look at a particular particle of this medium. We'll call it point A. Since this is a transverse wave, the particles of the medium are only going to oscillate up and down. Particle A is not a car on a roller coaster going up and down these hills. It's a particle of the medium, and it just vibrates up and down as this energy, the wave, travels to the right. We want to predict which way particle A will move in the next moment of time. A moment later, the wave will have shifted slightly to the right. Now remember, particle A can only move up and down, so it still has to be along this red dotted line. It should be obvious where particle A is now. It's at the top of this crest. Which way did it move to be on top of this crest? It moved up. If you need to predict the motion of a particle of a wave, ask yourself this question. Which part of the wave is coming next? If a crest is coming next, the particle has to move up to be on the crest. If a trough is coming next, then the particle has to move down to be in the trough. It really is as simple as that. Let's take a look at another example. Similar looking wave, traveling to the left. Here's particle A. Once again, transverse wave, particle A can only move up and down. In the next moment of time, the wave has shifted slightly to the left. Let's ask ourselves that question. If we're particle A, what part of the wave is coming next? Particle A is already on a crest. The next part of the wave that's going to get there is a trough. Which way do you have to move to be in a trough? You have to move down to be in a trough. Okay, enough of that. Let's talk about the Doppler effect. There's going to be a lot of audio-visual examples here and not that much to write down, so just pay attention to all the video clips. That's the Doppler effect. But what is the Doppler effect really?
Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect.
As Sheldon said, the Doppler effect is the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. Let's take a look at a few more examples.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
close. Meow.
A brain damage choo-choo train?
During the next few clips, I'm going to try to explain why the Doppler effect happens. There's nothing to write down, so just pay attention. The red dot in the center represents the source of sound waves. The blue rings and the blue lines on the graph below represent compressions in the sound waves. And you can see that the source is emitting them at a pretty constant rate, and observer 1 is detecting them at the same rate. Observer 2, all the way over there on the right, is also observing them at the same rate. This is happening because there's no relative motion. The observers are not getting closer to or farther away from the source of the sound. There's no Doppler effect happening in that example. Now let's take a look at what happens when the observers of the sound wave move. The red dot in the center, once again, is the source, and you can see that it's emitting the same sound waves as before, but look at observer 1 over on the left. Since it's moving away from the source of the sounds, those blue rings get to it very infrequently, and you can see on the graph below that the frequency is much less than the source. Observer 2, on the other hand, is moving toward the source, which means it's encountering those blue rings much more frequently than they're actually being emitted, and we can see that on the graphs below. Let's take a look at what happens when the source of the sound moves. That's like all those examples we saw with the moving train and the plane and the car. The red dot, once again, is the source, and it's emitting these waves at a constant frequency. But since it's moving to the right, the compressions on that side kind of get bunched up, and the compressions behind it kind of get stretched out. And so you can see that observer 1 intercepts those compressions less frequently than they are emitted, and observer 2 gets them much more frequently than they are emitted. It's important to note that the frequency of the source has not changed in any of these examples, but the apparent frequency, the observed frequency from observer 1 or observer 2, changes based on the relative motion between the source of the waves and that observer. Now let's write down a couple of notes about this. If the source of the sound and the observer are getting closer, that is, they have relative motion toward each other, then the apparent frequency of the wave will be higher. And it doesn't matter which one's moving, as long as they're getting closer together. If the source of the sound and the observer are getting farther apart, that is, they have relative motion away from each other, then the apparent frequency is going to be lower than the frequency that's actually being emitted. Finally, the greater the relative speed between the source and the observer, the greater the shift in frequency.
I still don't get it.
I'm the Doppler effect.
Okay, if I have some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra? Why don't you just tell people you're one of the 7 dwarves? Because I'm Frodo. Yes, well, I'm the Doppler effect.
Next, we'll talk about diffraction. Here's a cute stop-motion animation of diffraction. Diffraction is the bending of a wave around an obstacle, or the spreading out of a wave beyond an opening. Here are a couple diagrams. In both examples, we have those blue lines moving in from the right. We call those wave fronts. If these were water waves, you can imagine that each of those blue lines represents the crest of a water wave. When those waves reach the barrier, they can obviously only pass through in that small opening. But once they get through that opening, they spread out behind the barrier. There doesn't actually have to be a barrier with an opening. It can just be some obstacle like you see on the right. And so when the wave fronts get there, they obviously can't pass through the barrier, but the parts of the wave that do get past the barrier will spread out behind it once they pass. Listen to what this guy has to say about diffraction.
So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced.
So maximum diffraction occurs when the size of the opening is the same as the wavelength of the wave. Finally, we'll talk about natural frequency and resonance. The natural frequency of an object is the particular frequency that the object will vibrate if disturbed. When you pluck a guitar string, it vibrates at its natural frequency. Resonance is the vibration of a body at its natural frequency due to the action of a vibrating source of the same frequency. These two glasses are filled up to the same level, and when the glass on the right is disturbed and makes that obnoxious sound, the matchsticks on the glass on the left kind of wiggle around and then fall off. That's evidence of resonance. The vibration of the glass on the right causes the glass on the left to also vibrate. This lesson is about electromagnetic waves. Electromagnetic waves consist of electric and magnetic fields. They do not require a physical medium through which to travel. This means that they can travel through a vacuum. And unlike mechanical waves, which can be transverse or longitudinal, electromagnetic waves are transverse only. Here's a video clip that shows and describes electromagnetic waves.
Electromagnetic radiation is a form of energy that propagates through space as oscillating waves that have electrical and magnetic components perpendicular to one another.
The first thing we'll talk about is polarization. Polarization is the filtering of light based on the orientation of the wave. Being a transverse wave, light can be oriented vertically, horizontally, diagonally, literally an infinite number of orientations. And light from something like the sun or a light bulb comes at us in all different orientations. Some light is vertical, some's horizontal, some's diagonal. You can use a polarizer to eliminate all but one of those orientations, and this diagram shows that. We have vertically, horizontally, and diagonally oriented light going into the filter, and only vertically oriented light coming out. You may have polarized sunglasses that produce glare. This is how they work. You may have been to a 3D movie. This is how 3D glasses work. One of the lenses allows light of one orientation to pass through. The other lens only allows light of a different orientation to pass through. And when you get two slightly different images, one in each eye, your brain puts those together and gets a 3D image out of them. Here's a diagram of the electromagnetic spectrum. We often refer to electromagnetic waves as light. You can see in this spectrum that light, or what we would call visible light, is really just a tiny little sliver of the entire spectrum. The other types of electromagnetic waves range from gamma rays, having a very high frequency and short wavelength, to radio waves, having a very long wavelength and small frequency. We'll spend a lot of time in class practicing how to read this chart. When a wave reaches a boundary between two materials, there are three basic things that can happen. The first is absorption. That is, the electromagnetic waves are taken in by the atoms of the new medium. Another thing that can happen is reflection. That is, the electromagnetic waves can bounce off of the new medium. The last thing that can happen is transmission. This is when the electromagnetic waves travel past the boundary into the new medium. I don't want you to get the impression that only one of those things can happen. In fact, it's possible for all three of those things to happen at the same time. So some of the energy would be absorbed, some of the energy would be reflected, and some of the energy would be transmitted. In this lesson, we're going to focus on reflection. A lot of what you need to know about reflection is pretty intuitive. We use mirrors all the time, and I think we have a pretty good idea of how reflection works, but you will learn a couple things here that are new to you. Let's draw a diagram of a reflecting ray of light. So this horizontal line represents some reflective surface, and here is a ray of light. Instead of drawing squiggly lines to represent the transverse waves that are electromagnetic, we just draw a straight line, and we put an arrowhead in there. We don't always put the arrowhead at the end because we don't want our diagram to get cluttered, but we do need that arrowhead to show which way this ray of light is traveling. Since this ray is striking the surface, we call this the incident ray. To be incident upon something is to strike it. And we want to be able to describe the direction of this ray, and down to the right just doesn't cut it. There's a lot of other rays that would also be down and to the right. And so what we want to do, just like we did with vectors, is describe the direction of this ray by describing an angle. And for reasons that will become clear later on, we're not going to just measure the angle between the ray and the reflective surface. What we're actually going to do is draw a line perpendicular to the reflective surface right where the incident ray strikes it. And we're going to call this line a normal. Remember normal force? We describe normal force as a force that is perpendicular to the surface. Same thing here. This is the normal. Now this is an imaginary line. This is an array of light. We're just going to use this so we can measure an angle. The angle we care about is the angle between the incident ray and the normal. And we're going to call this theta I. This stands for angle of incidence. Now you probably won't be surprised when I show you the reflected ray. This is the part that's very intuitive. Just like we measure the angle of incidence, we want to measure the angle of reflection. I think it's pretty obvious from the diagram, and I think this is what most of you would expect anyway. If we measured theta I and theta R, we would find out that they are equal. And this is actually so important that it has a name. This is called the law of reflection. The incident angle is equal to the reflected angle. You can see in this demonstration that no matter what I make the incident angle, the reflected angle is always exactly the same. There are actually two types of reflection. The first is what you normally think of when you think of reflection. We call this regular reflection. You can see that the incident rays that are striking the surface are parallel to each other, and so are the reflected rays. This is exactly what you get when you look at a plane mirror or any other surface that produces an image. The other type of reflection is called diffuse reflection. Now, we actually encounter this reflection far, far, far more often. Diffuse reflection is happening anytime you can see an object. Literally anytime you see an object, diffuse reflection is happening. The way that we see things is that light from a light bulb or the sun reflects off of the object, bounces off of the object, and that light goes into our eyes. Look around the room. Anything that you look at, you can see because of diffuse reflection. Take a look at the diagram. The incident rays that are going to strike the surface come in parallel. Each individual ray reflects according to the law of reflection. That is, the incident angle and the reflected angle are equal. But since the surface isn't flat, the reflected rays go off in all different directions. That's why you don't see a reflection. You don't see an image when you look at the piece of paper that you're taking notes on. But you can see the piece of paper that you're taking notes on because some light is reflecting off of it and going into your eyes. Here's a demonstration of regular reflection. No matter what angle we set these at, they're parallel coming in and they're parallel going out. This would produce a reflected image. Here, the surface is uneven. The incoming rays are parallel, but the outgoing rays are kind of all over the place. This lesson is about refraction. Here are some things you need to know about electromagnetic waves. First of all electromagnetic waves travel at a speed that we call the speed of light. I don't think this is a great name for it, because this isn't only the speed of visible light, this is also the speed of gamma rays, X-rays, radio waves, and everything else on the spectrum when they are traveling in a vacuum. The speed of light is 3 times 10 to the 8 meters per second. That's 300 million meters per second. And this is abbreviated by the letter C. That's the C in E equals mc squared. In other materials like water or glass or any other material that light can travel through, light's going to travel at different, slower speeds, and we'll get to that in a moment. Something that's going to be important to keep in mind is that the frequency of the wave always remains constant. Light traveling in a vacuum is the fastest thing in the universe. Nothing can travel faster than light in a vacuum. Light does, however, travel slower when it's in a medium, in the material. Every material, every medium, has what's known as an index of refraction. Here's the table of indices of refraction right off your reference table. These are just a handful of the materials that light can travel through. If you go on the internet, you can find the index of refraction of many, many more materials. The index of refraction is an indicator of how much light slows down in that medium. The higher the index of refraction, the more the light slows down. Looking at the table again, we can see that light must travel the slowest in diamond because diamond has the highest index of refraction. Light would travel the fastest in air because it has the smallest index of refraction. The index of refraction is a ratio, which means it's unitless, of the speed of light in a vacuum to the speed of light in the material. Written as an equation, it looks like this. N, the index of refraction, equals C over V. Once again, C is the speed of light in vacuum, and V is the speed of light in whatever material it happens to be traveling through. Let's take a look at an example. What is the speed of light in quartz? Well, we start with N equals C over V. We can plug in the index of refraction of quartz, 1.46, and the speed of light in a vacuum, 3 times 10 to the 8 meters per second. We do a little cross multiplication and division, and we find that light travels 2.05 times 10 to the 8 meters per second in quartz. It's still really fast, 205 million meters per second, but it's still slower than light travels in a vacuum. Here's another example. Light is traveling at a speed of 2.26 times 10 to the 8 meters per second in an unknown medium. Let's figure out what that medium is. We can start once again with the equation N equals C over V, and we know that light always travels 3 times 10 to the 8 meters per second in vacuum, and in this material it happens to be traveling 2.26 times 10 to the 8 meters per second. This gives us an index of refraction of 1.33. Look on your reference table. What material is this? It's water! Now I'd like to take a look at some ratios. Ready for some algebra? We're going to compare the speed of light and the index of refraction of two different materials. You don't have to write anything down until the end, just try to follow along and make sure the math makes sense. So we can write for material 1, N1 equals C over V1. And for material 2, we can write N2 equals C over V2. Now let's turn this into a ratio of N2 over N1. All I did was take those two equations and basically divide them by each other. You can see that we're dividing by a fraction, so what we can do instead is multiply by the reciprocal. Hopefully you can see now that there's a C on the top and a C on the bottom, and so the C's cancel out. This leaves us with N2 over N1 equals V1 over V2. We're not done yet, but let's take a look at that. Do you notice that the n's are 2 over 1 and the v's are 1 over 2? That's because there's an inverse relationship between the index of refraction and the speed of light in the material. Let's go a little farther. The speed of a wave is the frequency times the wavelength. Since the frequency of the light doesn't change as it goes from one material into another, we don't have to write F1 and F2, it's just F. And since we have an F on the top and an F on the bottom, those can cancel out. This leaves us with our final set of ratios, N2 over N1 equals V1 over V2 equals lambda 1 over lambda 2. Like we've seen before, you would take two of these terms, based on what you're given and what you're trying to find out, and set them equal to each other. Now we finally get to refraction itself. These are all examples of refraction. When light traveled from air into glass or glass into water, the speed changed because the materials have different indices of refraction, and therefore the direction changed. That's what gives us those weird distorted images. Refraction, then, is the bending of light as it travels between two materials with different indices of refraction. Let's take a look at an example. This line represents the boundary between air and water. Here's an incident ray, and we'll describe the direction of this ray, like we did with reflection, by measuring the angle between the ray and the normal. This angle is called the angle of incidence, and we're going to call this theta 1. Now we know that light slows down when it goes from air into water. This is going to mean that the refracted ray is going to bend toward the normal. That is, the angle of refraction is going to be smaller than the angle of incidence. Here's another example. This time the line represents the boundary between glass and air. Once again, we have an incident ray. We'll measure the angle of this incident ray between itself and the normal. We'll call that theta 1, the angle of incidence. And now, when the light travels from glass into air, we know it's going to speed up. And when it speeds up, the refracted ray bends away from the normal. In this case, the angle of refraction, theta 2, is bigger than the angle of incidence. The relationship between the angles of incidence and refraction, and the indices of refraction of the two materials, are represented by an equation called Snell's law. This equation is N1 sine theta 1 equals N2 sine theta 2. Doesn't really matter which material you call 1 and 2, as long as the angle in that material and the index of refraction of that material go together. It would be a great idea to write this equation very prominently in your notes and to accompany it with this diagram. Let's take a look at an example. We have a ray of light traveling in air, striking a boundary with ethyl alcohol at an angle of 40 degrees. We want to figure out what's the angle of refraction in the ethyl alcohol. We can start with Snell's law, n1 sine theta 1 equals n2 sine theta 2, and we can plug in everything that we know. We can look up the indices of refraction on our reference table. Air is 1.00, and the angle in air is 40 degrees. The index of refraction of ethyl alcohol is 1.36, and the angle in ethyl alcohol is our unknown. We'll just leave it as theta 2. We can find that the sine of theta 2 equals 0.47, and then in our calculators we can do inverse sine of 0.47 to find out that theta 2 must be 28 degrees. If you're not sure how to do that math in your calculator, talk to me in class. There's a particular angle involved in refraction that's called the critical angle. This is the incident angle that results in a 90-degree angle of refraction. There's only a critical angle for a ray of light traveling from a material with a larger index of refraction to a material of a smaller index of refraction. Here's a diagram to represent what I mean. The critical angle is an angle of incidence represented by theta c, and the refracted angle is exactly 90 degrees. Total internal reflection is a phenomenon that can occur that involves the critical angle. Total internal reflection occurs when light is traveling in a medium with a high index of refraction and strikes a boundary with a material of lower index of refraction at an angle greater than the critical angle. You can see in this animation that when the incident angle is small, most of the light is refracted and some of it is reflected. When the angle gets too big and crosses the critical angle, all of the light is reflected, and it's reflected within the material itself, internally. So right about there is the critical angle. When the incident angle is larger than that, all of the light is reflected internally and none of it is refracted. This new unit is about electricity and magnetism. This first lesson is about the electrostatic force. We're going to start off with a little bit of review about the parts of the atom. Some of this you'll already know, and some of this will be new. What should definitely not be new to you are the three basic parts of the atom. All atoms in the universe are made up of protons and neutrons, which exist inside the nucleus of the atoms, and electrons, which exist outside of the nucleus. There are two basic properties of these particles that we need to be familiar with. The first is mass. Just like any other mass we've talked about in this course, the mass of these particles is measured in kilograms. Since you already know something about these particles, you won't be surprised to see how tiny the masses are. The proton and the neutron are both 1.67 times 10 to the negative 27 kilograms. That's about a billionth of a billionth of a billionth of a kilogram. The electron, as you know, is even smaller, 9.11 times 10 to the negative 31 kilograms. You can find all of these numbers on the first page of your reference tables. The other important property of these particles that we need to be familiar with is charge. One way to identify the charge of an object is to describe how many elementary charges it is composed of. Elementary here, like elementary school or elementary, my dear Watson, means basic, most basic in fact. The elementary charge is the smallest individual charge that can exist in the universe. Last year, and before that, if you described the proton as positive 1, what you meant was positive 1 elementary charge. Neutrons, as you know, are neutral, we can call that 0, and electrons you've called negative 1. And again, when you said an electron was negative 1, you meant it was negative 1 elementary charge. There will be plenty of situations where we describe the charge of the proton and the electron as simply positive or negative. Sometimes we'll include a little more information by describing them as positive 1 or negative 1, just like you've done before. However, if we're ever going to use the charge of the proton or the electron in an equation, we cannot use positive 1 or negative 1. Elementary charge is a description of how much charge there is. It's a comparison. It isn't a unit. The unit that we'll use for charge in this course is the coulomb. This is named after a French physicist whose name I can't properly pronounce. 1 elementary charge is equivalent to 1.6 times 10 to the negative 19 coulombs. This means that a proton is positive 1.6 times 10 to the negative 19 coulombs. A neutron is still just 0 coulombs, it's neutral, and an electron is negative 1.6 times 10 to the negative 19 coulombs. Again, if we ever need to use the charge of a proton or an electron in a calculation, we have to use the charge of these particles in coulombs. We cannot simply use +1 and -1. The next thing we should discuss is the charge on an object. We're going to start this with a couple of basic facts. First of all, atoms are normally neutral. That is, they have the same number of protons and electrons. Another really basic fact is that all macroscopic objects are made of atoms. Macroscopic is the opposite of microscopic. Microscopic objects are things that you cannot see with the naked eye. Macroscopic objects are things you can see with the naked eye, so look around. Anything you can see is macroscopic, and all of those things are made of atoms. If we take these two basic facts together, we should be able to say that all macroscopic objects are normally neutral. The universe would be a pretty boring place if everything was always neutral, however. Objects can become charged. And there are two really fundamental ways that this can happen. An object can gain electrons to become negatively charged, or it can lose electrons to become positively charged. There is no other way for an object to become charged. Atoms cannot gain or lose protons. Since the charge on an object depends on how many electrons it gained or lost, the charge of an object must be a multiple of the charge of an electron. That is, it has to be a multiple of 1.6 times 10 to the negative 19 coulombs. Let's take a look at a couple examples. Let's say that a balloon was rubbed against someone's hair, and the balloon gained 9 electrons. What's the charge of that balloon going to be in coulombs? Well, this is the perfect situation to use a proportion. Well, we know that one elementary charge is 1.6 times 10 to the negative 19 coulombs. In this problem, we're dealing with 9 elementary charges because the balloon is gaining 9 electrons. How many coulombs is that equivalent to? Well, in this case, all we have to do is cross-multiply, and we'll find that 9 elementary charges is equivalent to 1.44 times 10 to the negative 18 coulombs. When we talk about the charge of an object, we should state the sign of the charge in addition to the magnitude. Since this balloon gained 9 electrons, it must actually have a negative charge. Here's another example. A metal sphere has a charge of positive 4.8 times 10 to the negative 19 coulombs. First, did it gain or lose electrons? And how many? Well, if we take a look at the sign of the charge, we can see that it's positive. If an object is positive, that means it has more protons than it has electrons. The only way for that to happen is for the object to lose electrons. Once again, we'll set up a proportion to figure out how many electrons it lost. So one elementary charge is 1.6 times 10 to the negative 19 coulombs. We want to know how many elementary charges 4.8 times 10 to the negative 19 coulombs is equivalent to. If we cross multiply and divide, we find out that this is equivalent to 3 elementary charges, and therefore 3 electrons lost. The next thing we want to look at is the interaction of charged particles. We'll start by discussing attraction and repulsion. So this picture shows two objects that each have a net positive charge. You should already know how these two particles should interact. Two objects with positive charge should feel force away from each other, and if they were free to move, they would actually repel. Here are two other objects. Each of these has a net negative charge. This means that each of them must have gained electrons. Just like the two positive objects, these two negative objects will also feel a repulsive force, and if they were free to move, they too would repel from each other. Finally, we can take a look at an object with a net positive charge and an object with a net negative charge. These two objects will feel an attractive force between them. If they were free to move, they would attract each other. To summarize this, like charges repel, and opposite charges attract. The strength of this attraction or repulsion is determined by Coulomb's law. This is an equation that allows us to calculate the strength of the electrostatic force. Coulomb's law states that the force between two charged particles is directly proportional to the magnitude of the charges of the particles. So here we have two objects. One is negative 1 elementary charge and one is negative 2 elementary charges. And since they have the same charge, these two objects will repel each other. However, if we had two other objects of negative 8 elementary charges and negative 9 elementary charges, these will also repel, but since they have more charge, they will repel more strongly. Before we move on, I want to note that in each of these cases, both objects experience the same amount of force. This is Newton's third law. When two objects interact, they feel forces that are equal in magnitude and opposite in direction. Coulomb's law also states that the force between two charged particles is inversely proportional to the distance between the particles. So here we have those same negative 8 and negative 9 elementary charge particles, and when they're close, they'll feel a very strong repulsive force. However, if we move them farther away, the repulsive force that they experience will be much smaller. We can put these two relationships together with a constant to form an equation. This is the equation known as Coulomb's law. Fe equals K Q1 Q2 over R squared. Fe stands for electrostatic force. Just like every other force we've learned about this entire year, the electrostatic force is measured in newtons. K is the electrostatic constant. It is equal to 8.99 times 10 to the 9 Newton meter squared per coulomb squared. Just like every other constant, you can find this on the first page of your reference tables. Lowercase q is the abbreviation for charge. Q1 and Q2 in the equation refer to the charges of object 1 and object 2. And R stands for the distance between the centers of the objects. This is just like the R in the universal law of gravity. Let's look at some examples using Coulomb's law. Here we have two objects, one with a charge of positive 6 coulombs and one with a charge of positive 3 coulombs, and they're 12 meters apart. My question is, how much electrostatic force do they feel? Well, we start off with Coulomb's law, and we can plug in all of our givens, the constant from the reference table, the 6 coulombs and the 3 coulombs, and the 12 meters, which of course we square. When we carefully plug these numbers into our calculator, we find out that the electrostatic force between these two particles is 1.12 times 10 to the 9 newtons. Try it yourself and make sure you get the same answer as me. What the equation doesn't make clear is whether this force is attractive or repulsive, but that's fine. We don't need the equation to tell us that. Look at the two objects. They're both positively charged. Are these two objects going to attract or repel? Well, they are like charges, so they will repel. Here's another example. One object has a charge of positive 7 coulombs, and the other object has a charge of negative 4 coulombs, and these two objects are 0.25 meters apart. Once again, I want us to calculate how much electrostatic force each of them will experience. We'll go through the same process. We start off with the equation for Coulomb's law, and then we can plug in all of our givens. There's something really important I want to point out here. You'll notice I did not plug in positive 7. I mean, you don't really have to plug in a positive anyway. But more importantly, I didn't plug in a negative 4 coulombs. The positive and negative that we use to describe the different types of charge don't have the same mathematical connotations they usually do. In fact, instead of calling them positive and negative, we could have called the two different types of charge red and blue, or happy and sad. If an object had more happy charges than sad charges, it would have a net happy charge. If it had more sad charges than happy charges, it would have a net sad charge. Two objects with a net happy charge would repel, as would two objects with a net sad charge. An object with a happy charge and an object with a sad charge would attract each other. I know that's silly, but I'm really trying to make the point that when you use these charges in an equation, you don't need to include the positive and the negative. In fact, I think if you do, it might be more confusing than it is helpful. Let's finish off this equation, and we'll talk a little bit more about it. When we plug these numbers carefully into our calculator, we'll find that the electrostatic force between these two particles is 4.03 times 10 to the 12 newtons. That is the magnitude of the force that each of these particles will feel. Since force is a vector, we might also want to describe the direction. Here's where the positive and negative come in. Looking at these two objects, one's positive and one is negative, so we can say that the positive 7 coulomb charge will feel that force to the right, and the negative 4 coulomb charge will feel that force to the left. We don't need to include the positive and negative sign into the equation to come to that conclusion. We can discuss this more in class if we need to. This lesson is about conservation of charge. Conservation of charge is the idea that the total charge of a system is conserved. And remember, a system is just a group of objects and their interactions. This is similar to conservation of energy and conservation of momentum. I think this conservation law is the most intuitive. Since the net charge of an object depends on its number of protons and electrons and electrons can't just disappear or appear out of nowhere, the total charge has to be the same. There's always the same number of protons and electrons. There's a list of basically two ideal states for a system of multiple objects. The first one is that all the objects would have a net neutral charge. So throughout the whole system, there's the same number of protons and electrons, and each object also has the same number of protons and electrons. That's not always possible, though. So the next most ideal state would be for the net charge of the entire system to be equally distributed among all the objects. So rather than having many neutral objects and one that is very, very negative, it would be more ideal to have that really negative charge just spread out evenly among all the objects. These ideal states are achieved by the transfer of electrons, and as you would expect, they're going to transfer from objects of higher concentration of electrons to objects of lower concentration of electrons. Throughout this discussion, it's going to be very important for us to remember that protons do not transfer from one object to another, only electrons. The rest of this video consists of mostly diagrams and animations. I do not suggest that you try to copy all of them into your notebook. Just pay attention to what I'm showing you and try to see if it makes sense. This large white outlined circle is how I'm going to represent macroscopic objects in the following diagrams. Inside of this object, protons are going to be represented by blue squares, and electrons are going to be represented by purple circles. To help make the following concepts more understandable, I like to make an analogy between the charged particles in an object and the seats and passengers in train cars. The protons, which remain in a fixed location, are analogous to seats on the train. The electrons, which are free to move around and don't really want to be near each other, are analogous to passengers on the train. Let's take a look at our first example of conservation of charge. Here we have an object with a net charge of positive 3 elementary charges. You can see that there's 3 more protons than electrons. Here's another object with a net charge of negative 3 elementary charges. Here, there are 3 more electrons than protons. The law of conservation of charge does not require that the charge of either of those objects remain the same. What it does require is that the total charge of the system remain the same. Right now, you can see that the total charge of the system is 0. Within the entire system, there's the same number of protons and electrons. Now remember, the most ideal state is one in which every object in the system has a net neutral charge. The same goes for our analogy of train cars. It's ideal to the train company that every seat have a passenger in it, and it's ideal to the passengers that every passenger have a seat. Right now, these objects are too far apart for any electron transfer to occur. In order for that to happen, they would need to be very close to each other, or, better yet, they could be touching. Assuming that these objects are conductors of electricity, the electrons are now free to transfer from one object to the other. Electrons are going to transfer from the object with a higher concentration of electrons to the object with a lower concentration of electrons. So the excess electrons in the object on the right are going to transfer to the object on the left, like this. You can see, as the electrons transfer, that the charge of each object is changing. If you keep an eye on it, though, you should see that the total charge is actually remaining the same. Now we have 2 objects, which are each neutrally charged. Each one of them has the same number of protons and electrons. This is that first ideal state. If you think of our analogy, we now have a person for every seat and a seat for every person. And to go back to the conservation of charge, we can see that the total charge of the system is still 0. Let's take a look at a slightly more complicated system. Here we have an object on the left with a net charge of positive 6 elementary charges, and an object on the right with a net charge of negative 2 elementary charges. Let us note that the total charge of the system is positive 4 elementary charges. If we bring these objects in contact with each other, it should be obvious that the excess electrons on the right will transfer to the left. Now we have an object on the left with a net charge of positive 4 elementary charges, and an object on the right that is neutral. This isn't that first ideal state, though. The first ideal state was that every object in the system would be neutrally charged. That's just not possible here. Therefore, electrons will continue to transfer until the second ideal state is reached. Remember, that second ideal state is that the net charge of the system is equally distributed among all the objects. This means that more electrons will transfer until there's an equal number on each object. Let's think of our analogy. Imagine you're sitting on the train next to a person who is talking loudly on the phone, or they're snoring, or they smell bad, and you glimpse through the doors into the next car and you see a whole row of seats that are empty. The next time you get the chance, aren't you going to move over and have a row to yourself so you can spread out? I would. So 2 more electrons are going to transfer from the object on the right to the object on the left. We now have 2 objects that each have a net charge of positive 2 elementary charges, which is the most ideal system we could end up with in this case. Once again, let us note that the total charge is still positive 4 elementary charges. There's still the same number of protons and electrons in the system, it's just that the electrons were redistributed. Let's look at one more example. Again, this one is a little bit more complicated. Here we have an object on the left with a net charge of positive 3 elementary charges, and an object on the right with a net charge of negative 7 elementary charges. The total charge of this system is negative 4 elementary charges. When these 2 objects come in contact, at least 3 electrons are going to transfer from the right to the left. Like we saw before, we now have a neutral object and an object that still has a net charge. This is not an ideal system. Even though the object on the left now has a net neutral charge, some of the electrons on the right are still going to transfer over so that they can be more spread out. Let's think of our analogy again. Let's say you're coming home from the city after a concert or sporting event, and the train is packed. Every seat is taken, and lots of people are standing up, including you. You're in a train car where the standing people are packed in like sardines. You can barely move. You see, in an adjacent car, that although all the seats are taken, there are only a few people standing, and they look more comfortable and more spread out. When you get the chance, you might go over to that car yourself, even though you still have to stand, just to get a little bit more space between you and all the other people in the car. To finish up, we now have 2 objects that each have a net charge of negative 2 elementary charges, and the total charge is still negative 4 elementary charges, just like we started with. Let's take a look at one more example to see how the distribution of charge within an object can affect its interactions with other objects. Let's use for this example the pith ball. You should have used the pith ball in class. It's a little metallic coated styrofoam ball on a string. And this is just one example. A lot of the other phenomena that you'll see in class happen basically the same way. We're starting off with a neutral object. It has the same number of protons and electrons. What we're going to do is bring a very negatively charged object nearby. When we do, watch how the electrons inside the pith ball react. The electrons are repelled by the really negative object we brought in on the left. And so, since they're able to move, they redistributed themselves within the pith ball and moved over to the right. The pith ball still has a net charge of 0. There's still the same number of protons and electrons. But now they're not evenly distributed. Although the entire pith ball is neutral, you can see that the left half of the pith ball now has a net positive charge, and the right half of the pith ball has a net negative charge. Coulomb's law states that the left side of the pith ball would feel an attractive force, and the right side of the pith ball would feel a repulsive force. These 2 forces don't cancel each other out, however. Since the positive side of the pith ball is closer than the negative side of the pith ball, the attractive force is stronger than the repulsive force. This means that the pith ball feels a net force to the left, and will be attracted to that negative object we've brought nearby. Think about that for a second. You know that a negative object is going to attract a positive object, but did you ever think that a negative object would attract a neutral object? Do you think a positive object could also attract a neutral object? We can make this even more interesting if we let that negative object touch the pith ball. Now that they're in contact, electrons can transfer. There's an incredible excess of electrons on that object to the left. So just like we saw before, they're going to transfer to that area of lower electron concentration, that is, the left half of the pith ball. As you can see, the pith ball now has more electrons than protons, and therefore has a net negative charge. How are 2 negative objects going to interact? Well, they repel each other. This lesson is about electric fields. Let's start off with a couple of examples. Here's an object with a net positive charge. Let's imagine that we bring another charged object nearby, and let's also imagine that this object is also positively charged. If we place the second charge above, it would feel a force upward. If we placed it below, it would feel a force downward. If we placed it on the right, it would feel a force to the right. If we placed it on the left, it would feel a force to the left. And any other place that we put the second object, it will feel a force away from the large object in the center. This leaves us with an electric field diagram that looks like this. I suggest sketching that in your notes. One more example. Here's a negative object. And again, I want us to imagine that we're going to bring a second charged object nearby, and like before, we're going to imagine that it's a positive charge. If we put a positive charge below this, it'll feel a force up. If we put it above, it'll feel a force down. If we put it on the left, it'll feel a force to the right. If we put it on the right, it'll feel a force to the left. Any place we put this positive charge, it will feel a force toward our negative object. This leaves us with an electric field map that looks like this. An electric field is an area in which a charged particle will feel an electrostatic force due to the presence of another charged particle. Like we just did, we map electric fields with electric field lines. And as you saw, they're actually arrows. Electric field lines are based on the direction in which a positive test charge would feel force. That's exactly what we just did in our previous two examples. Why are electric fields based on a positive test charge? Well, because. Seriously, that's the only answer I can give you. It is a convention in physics. Someone in the 1800s decided that we would base them off of a positive test charge. They could have just as easily decided that they would be based off of a negative test charge, but they didn't. Anyway, moving on. Here's a more complicated electric field. No matter where we place the positive test charge is going to feel two forces. It's going to feel an attractive force to the negative object, and it's going to feel a repulsive force from the positive object. I want to go through this a little bit quickly to save time. I'm going to show the placement of the positive test charge. I'm going to show you the force that it would feel from each of those two charged objects that you see now. And then I will show the resultant of those two forces. Once we have the resultant force on the positive test charge at a variety of locations, we'll be able to map the electric field. If we place it right in the middle, it feels an attraction to the left and a repulsion to the left. If we place it on the right, it feels a repulsion to the right and an attraction to the left. If we place it on the left, it feels a repulsion to the left and an attraction to the right. That's the basic idea. We could do many, many more of these, but it's not really worth our time. I think with these few data points, we can figure out the basic map of this electric field. It looks something like this. What if we had two positive objects? Well, right in the middle, the positive test charge would feel a repulsion in both directions, and they would be the same magnitude, so they would cancel each other out. There's essentially no electric field right there in the middle. But at any other place, there will be a net force. Again, we could look at many more points, but this is enough to get the basic idea of this electric field. If we change the two objects to both be negative, the shape of the electric field map is not really going to change. What will definitely change is the direction that the arrows are pointing. Since electric fields are always based off of a positive test charge, the arrows should point away from positive charges, but they should point toward negative charges. Here are a couple statements we could make to summarize what we've learned about electric fields. Field lines always point away from positive charges, and field lines always point toward negative charges. Finally, and this may not have been obvious from our diagrams, field lines do not cross each other. That was the qualitative part of electric fields, and now on to the quantitative part. Let's include some numbers. Different electric fields can have different strengths, and even within an electric field, different points can have different strengths. The electric field strength is a ratio of the force exerted on a particle in the field and the charge of the particle. Written as an equation, we have E equals Fe over Q, where E stands for electric field strength. This is often described as electric field intensity. Fe, as you know, is the electrostatic force, and Q is the charge. Let's take a look at an example. When placed in an electric field, a small metal sphere with a charge of positive 6.3 times 10 to the negative 6 coulombs experiences a force of 5.67 times 10 to the negative 5 newtons. What is the strength of the electric field? As always, we start with the equation. We can plug in our force and our charge, and we can find that the electric field strength is 9 newtons per coulomb. There's no special unit for this, it's just newtons per coulomb. Here's another example. How much force will be exerted on a particle with a charge of negative 8.7 times 10 to the negative 9 coulombs if it is placed in an electric field with a strength of 2.6 newtons per coulomb? There's one more thing we need to talk about that's related to electric fields. So as we've seen, a charged object in an electric field feels a force. Either the force of the electric field or an external force can cause the charged object to move. Right? If it's moving, that means it has a displacement. So for example, here we have a positive charge, and you can see the electric field around it. And if we put another positive charge at point A, the electric field itself would exert a force in that direction. If the particle at point A was free to move, it could have a displacement and end up at point B. Similarly, if the object were at point B, someone or something could exert a force on it toward point A, causing it to have a displacement. In either of these cases, we have the object feeling a force and having a displacement. This means that work is done. This brings us to the concept of potential difference. The amount of work required to move a charged object depends on two things. It depends on the magnitude of the charge itself, because that will affect the amount of force it feels. And it depends on what we call the potential difference between the two locations. This is kind of like height for gravitational potential energy. If you want to figure out how much gravitational potential energy an object gains, you need to know the mass of the object, and you have to know the height that it's gaining or losing. The equation for the work done on an object in an electric field, then, is W equals V times Q, where W stands for work, V stands for potential difference. We use V because this is also called voltage, more on that later, and Q, of course, stands for charge. On your reference table, it's actually written as V equals W over Q. Let's take a brief look at the units. If we plugged in an amount of work and an amount of charge, we would plug in joules over coulombs, and we would get joules per coulomb, and that's perfectly appropriate. This, however, has a special name. A joule per coulomb is called a volt. You've definitely heard about volts before. Here's an example. In order to move an object with a positive 1.8 times 10 to the negative 6 coulomb charge between 2 points in an electric field, 5.4 times 10 to the negative 6 joules of work must be done. What is the potential difference between these points? Well, V equals W over Q. We can plug in the work done and the charge of the particle, and we can find that the potential difference between these points is 3 joules per coulomb, otherwise known as 3 volts. Here's another example. A charged particle is moved between 2 points in an electric field with a potential difference of 1.5 volts. Moving the particle required 7.05 times 10 to the negative 3 joules of work. What is the magnitude of the charge of the particle? This lesson is about current electricity. I'm going to let my man Bill Nye start us off.
Well, electricity is the flow of tiny particles called electrons. And they're not just smaller than atoms, they're actually part of atoms. Take a look at this. It's our battery-powered electrical circuit of science. We're going to run this big light with this big battery. Watch. See, right now, electrons can flow from this side of the battery, through this wire, through the switch, through this wire, into the light, and back to this side of the battery. They're flowing in a closed path, what scientists call an electrical circuit. Now, circuit, that's from an old word for go around. So electrons, right now, can go around an electrical circuit. The flow of electrons is a lot like the flow of water. Now get it. Watch. When I operate this great big water pump of science, water goes through this hose, into this box, and makes this water wheel go around. And it goes out the other side, and through this hose, back to the pump. It's a closed path for the flow of water. It's a water circuit. It's just like the flow of electrons through an electrical circuit.
Bill's analogy to water flowing through a hose is very helpful when learning about electricity. Whether I mention it or not, if you're having trouble understanding a concept related to current electricity, imagine the situation as if it were water molecules flowing through a hose instead of electrons flowing through a wire. Let's start off by defining current. Current is the rate at which charge flows. I is equal to charge divided by time. I stands for current, Q is charge, and T is time. Let's take a look at the units. If we plugged in a charge and a time, we would end up with coulombs per second, and that's perfectly appropriate. I think coulombs per second makes a lot of sense. However, we have a special name for this. A coulomb per second is also known as an ampere, abbreviated with a capital A. This is often called an amp. Let's take a look at an example. In 1 minute, 0.3 coulombs of charge pass through a copper wire. What is the current in the wire? Well, we start with our equation. We know we have 0.3 coulombs, and we have 60 seconds. Not 1 minute, 60 seconds. Here we can see that our current would be 0.005 amps, which would also be known as 5 milliamps. Here's another example. How much charge passes through a wire in 20 seconds if there's a current of 2.5 amperes? Let's revisit conservation of charge and see how this applies to current. Since charge is a conserved quantity, and the current is the rate at which charge flows, then current must also be conserved. This is called Kirchhoff's first law. At any junction in an electrical circuit, the sum of currents flowing into that junction is equal to the sum of currents flowing out of that junction. Here's an example. The junction is that circle in the middle, and if you look at the two currents I1 and I2, you can see that there are 9 amps flowing into the junction. If you look at I3, you can see that there's 8 amps flowing out of the junction. Well, if there's 9 amps flowing in, there has to be 9 amps flowing out. Since we only see 8 amps flowing out in I3, then I4 must be 1 amp flowing out. Now we have 9 amps flowing in and 9 amps flowing out. Here's another example. I1 is 15 amps flowing out of the junction. I2 is 9 amps flowing out of the junction. What would I3 be? Electrical resistance. When electrons travel through any component of a circuit, their rate of flow is reduced. Each component has a property called resistance, even the wires. The resistance of a wire, such as the filament of a light bulb, depends on a few of its physical properties. First of all, the resistance of the wire is directly proportional to the length of the wire. Think about it like this. It's harder for electrons to get through a long wire than it would be for them to get through a short wire. The resistance of a wire is inversely proportional to the thickness of the wire. The thicker the wire, the easier it is for electrons to flow. The quantity that we actually use that's related to the thickness of a wire is called the cross-sectional area. If you took a wire and cut it in half and then looked at the end, you'd see a circle, and that circle would have an area. The resistance of a wire is inversely proportional to that area. Remember, the area of a circle is pi r squared, and they actually remind you of that on your reference tables. Finally, the resistance of a wire depends on what material it's made out of. Wires can be made out of copper, or gold, or silver, or a variety of other metals. Each material has a property called resistivity. This is abbreviated by the Greek letter rho. The resistance of a wire is proportional to the resistivity of the metal that it's made of. You can look up the resistivities of certain metals on your reference tables. If we put those relationships together to get an equation, we end up with R, the resistance, equals rho L over A. Let's take a quick look at the units for all of these quantities. Length, as you might suspect, is measured in meters. The cross-sectional area is meters squared. Resistivity is measured in ohm meters. And when you put all those together, resistance is measured in ohms. That symbol is the Greek letter omega. Let's take a look at an example. A 5-meter long copper wire has a diameter of 3 millimeters. First, what is the cross-sectional area of the wire? Well, area is pi r squared, and radius is half of the diameter. So if the diameter is 3 millimeters, the radius is 1.5 millimeters. As always, we don't want millimeters, we want meters. We can change that to 0.0015 meters. When we square that and multiply by pi, we should get 7.065 times 10 to the negative 6 meters squared. Now we can determine the resistance of the wire. R equals rho L over A. We can look up the resistivity of copper on the reference table. It's 1.72 times 10 to the negative 8 ohm meters. We know that the wire is 5 meters long, and we just found out the cross-sectional area. The resistance of this wire would be 0.012 ohms. Here's another example. A 2.5 meter long silver wire has a diameter of 2 millimeters. What is the cross-sectional area of the wire? What is the resistance of the wire? This lesson is about simple circuits. Let's talk about voltage. Electrons don't just flow through a wire for no reason. There are 2 requirements for electrons to flow. First, they have to have somewhere to go. The circuit has to be closed. There also has to be something to push them through the circuit. A battery, or a source of potential difference, or a voltage source, all the same thing, provides that push. This is sometimes referred to as electric pressure, like the water pressure in a hose that pushes water through it. Let's take a look at a very simple circuit. Here we have a battery connected to a resistor with a few wires. A resistor is a very common electrical component that is used to regulate the amount of current in a circuit. All it does is take electrical energy and convert it into heat. Instead of a resistor, we can have a light bulb in the circuit. This brings us to Ohm's law. The current through a wire is directly proportional to the voltage applied to it. The current through a wire is inversely proportional to the resistance of the wire. When we put these together to form an equation, we find that I equals V divided by R. If we cross multiply, we get V equals I times R. And if we divide both sides by I, we end up with the form of the equation that you'll find on your reference table. R equals V divided by I. They're all the same equation. Use whichever one you like. This last one is on the reference table. Let's take a look at an example. How much current will flow through a 12 ohm resistor when it is connected to a 9 volt battery? We'll start with the equation from our reference table. We can substitute in the 12 ohms and the 9 volts, and we can find that the current would be 0.75 amps. Here's another example. When the light bulb in a flashlight is connected to a 3 volt source of potential difference, a current of 0.4 amps flows through it. What is the resistance of the light bulb? I already mentioned electrical energy. Let's talk a little bit more about that now. When a light bulb is lit, or when an electric motor is running, or when your phone is charging, electrical energy is being used and work is being done. I want to show you where a couple of really important equations come from. You definitely do not need to write this down. Just take note of the final equations that have red boxes around them. Here's the equation we learned a while ago for potential difference. We could rearrange this equation and solve it for work. Here's the equation for current. We could rearrange this equation so it is solved for Q. Now we want to put these together. If Q equals I times T, then W could equal V times I times T. So here's W equals VIT, and here is the form of Ohm's law, V equals IR. If we put these together, we could say that W equals I squared RT. There's that first work equation again, and here's another form of Ohm's law. If we put these two together, we can say that work equals V squared over R times T. We now have 3 expressions for work, and here they are all together. You will find this equation on your reference table. Let's take a look at an example. An electric hairdryer is plugged into a 110 volt source and draws a current of 17 amps. How much electrical energy does the hairdryer use in 1 minute? If we made a list of givens, we would see that we know the voltage, the current, and the time. This means we should use the form of the equation W equals VIT. If we plug in our givens and multiply, we'll see that 112,200 joules of work is done when this hairdryer runs for 1 minute. Here's another example. An electric motor with a resistance of 150 ohms uses 1.8 times 10 to the 6 joules of energy in 30 seconds. How much current was flowing through the motor? If you're not sure where to start, make a list of givens to figure out which equation to use. As you know, work is related to power. Power, remember, is the rate at which work is done. Also, we could say that it is the rate at which electrical energy is used. Here comes some more algebra. Remember, you don't have to write down every step. Just write down the conclusion. So power equals work divided by time. That's from months ago. We just learned a series of equations for W. This is going to look silly, but we could take that entire series of equations for W and plug it in to the equation above. This gives us P equals VIT equals I squared RT equals V squared over RT, all over T. You may have noticed that each term on the right has a T, and we're dividing by T. This really simplifies things. All those T's cancel out, and we're left with the equation P equals W over T equals VI equals I squared R equals V squared over R. And again, this is on your reference tables. Let's take a look at an example. How much current flows through a 60-watt light bulb when it is connected to a circuit with a voltage of 110 volts? Since we know the power and the voltage, and we're looking for current, we can use the form of the equation P equals VI. If we plug in our givens, we can find out that the current through the light bulb is 0.55 amps. Here's another example. A typical hairdryer has a power of 1,875 watts. If it is connected to a 220 volt source, what is the hairdryer's resistance? Again, if you're not sure where to start, make a list of givens to figure out which equation to use. This lesson is about series and parallel circuits. There are two basic ways to connect multiple components of a circuit. They can be connected in series, which means that there's one path for electrons to flow. Electrons will travel through every component. The other way we could connect multiple components is in parallel. This means that there are multiple paths for electrons. Electrons only travel through one component or another. Let's begin with series circuits and discuss potential difference or voltage. Electrons now are going to be passing through multiple components. The electrons gain electric potential from the battery. This is just like a chairlift, which gives skiers gravitational potential energy. Electrons are going to lose electric potential through or across each component. This is like skiing down each section of a trail. You'll lose some gravitational potential energy on each section. This means that the sum of the potential differences at each component should be equal to the potential difference of the battery. For series circuits, V equals V1 plus V2 plus V3. Now let's look at current. The electron flow, the current, originates at the battery. Since there's only one path, all the electrons have to flow through all of the components. If 100 electrons come out of the battery, then all 100 electrons travel through the first resistor, and then all 100 travel through the second resistor, and then all 100 travel through the third resistor. The current in a series circuit is the same through each component. Finally, let's talk about resistance for series circuits. Since each electron has to travel through every component of a circuit, as more components are added, the overall resistance of the circuit would increase. This is also known as equivalent resistance. The equivalent resistance in a series circuit is simply the sum of the individual resistances. Now let's take a look at parallel circuits. We'll start with potential difference or voltage. Once again, electrons gain electric potential from the battery. But this time, electrons are only passing through one component. Therefore, they have to lose all their electric potential through that single component. If you and two friends are going snowboarding, you gain the same amount of gravitational potential energy as you go up the chairlift. And even if one of you takes a beginner trail, and one of you takes an intermediate trail, and one of you takes an expert trail to the bottom, you'll all lose that same amount of gravitational potential energy. In a parallel circuit, the potential difference across each component is the same. Now let's take a look at current. Once again, the current originates from the battery. Each electron is only going to pass through one component or another, so some of the total current passes through each of the components. This means that the current originating from the battery is equal to the sum of the individual currents. Finally, let's talk about resistance in a parallel circuit. When more components are added in parallel, the electrons have more possible paths to follow. This is like opening up more lanes on a highway. This reduces the overall or equivalent resistance. It's not easy to write an equation that shows the sum getting smaller as you add more numbers. This means that the equation for equivalent resistance in a parallel circuit is a little bit complicated. The reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. Let's take a look at an example of a resistance calculation. I want to point out a common mistake that people make so that you don't make it. What is the equivalent resistance of a parallel circuit with 3 resistors, 4 ohms, 6 ohms, and 10 ohms? Well, we can start with our equation for equivalent resistance in a parallel circuit, and we can plug in our 4, 6, and 10 ohms. If we do the addition on the right, we can find that the reciprocal of the equivalent resistance is 0.52. This is not the answer. The question doesn't ask for the reciprocal of the equivalent resistance. We want to know the equivalent resistance. You could use the reciprocal button on your calculator that looks like a 1 divided by x, or you could put the 0.52 over 1 and cross multiply and divide. Either way, you'll find that the equivalent resistance is 1.94 ohms. Please make sure that you do this last step if you're trying to solve for the equivalent resistance of a parallel circuit. Here's another example for you to try. What is the equivalent resistance of a parallel circuit with 3 resistors, 12 ohms, 20 ohms, and 32 ohms? Now that we know the equations for series and parallel circuits, we can use them to calculate the voltage, current, and resistance of circuits and components of circuits. To help us do this, we're going to use the magic table. Okay, it's not magic, obviously, but it's incredibly helpful. I'm going to explain how to use it, and I think that you'll find that it's a great way to organize your information, and it can help you figure out which equations to use. First, let's describe the table. There's a column for each quantity: voltage, current, and resistance. I've written them in this order because V equals IR. There's a row for each component of the circuit. If there's 3 resistors, you have rows 1, 2, and 3. If there's 2 light bulbs, you just have rows 1 and 2. If there's 4 electric motors, you have rows 1, 2, 3, and 4. Finally, there's a row for the circuit as a whole. Let's take a look at an example and go over the directions for how to use the table. So here's a parallel circuit with a 12-volt source of potential and 3 resistors, 2 ohms, 4 ohms, and 6 ohms. I want us to figure out the total current of the circuit and the current through each resistor. So first of all, draw a table. Next, we fill in our givens. The next step might seem trivial, but it's actually pretty important. Identify the type of circuit that we're dealing with. This is clearly a parallel circuit. I suggest covering the series circuit equations on your reference table with your calculator so you don't even see them. Finally, we'll use appropriate circuit equations to fill out the columns and rows. Since this is a parallel circuit, we should know that the potential difference across each resistor is the same as the potential difference of the source. All of the V's are 12. Now, we can use Ohm's law across each row to figure out the current. I times R has to equal V. So 6 times 2 equals 12, 3 times 4 equals 12, and 2 times 6 equals 12. We've now found the current through each of the resistors, and if we simply add those up, we can find the total current in the circuit. Notice we were not asked to find the equivalent resistance of the circuit. If we wanted to, we could find it one of 2 ways. We could say that R equals V divided by I and do 12 divided by 11, or we could use the equivalent resistance equation for a parallel circuit and use the 2, 4, and 6 ohms. Either way, we would find that the equivalent resistance of the circuit is 1.09 ohms. Here's another example. You try this one. What is the total current in the circuit, and what is the potential difference, or voltage, across each resistor? Hint: use the table. This lesson is about magnetism. Magnetism is caused by the motion of charged particles. In a permanent magnet, like the ones that stick on your fridge, the magnetism is caused by the motion of electrons around the nucleus of each atom. In an electromagnet, like the ones that hold the doors open in the school, the magnetism is caused by the motion of electrons through a wire. There's a lot you should already know about magnets. Every magnet has 2 poles, a north pole and a south pole. Based on their orientation, these 2 magnets would attract each other. These 2 would repel. These 2 magnets would attract, and these would repel. Like poles repel each other, opposite poles attract. It is not possible for an isolated north pole or an isolated south pole to exist. They always come in pairs. If we take this long bar magnet and cut it in half, we get 2 smaller complete bar magnets, each with a north and south pole. We can keep cutting these magnets in half and ending up with complete bar magnets with both north and south poles until we end up with individual atoms. If this bar magnet was made of iron, we would eventually end up with a whole bunch of iron atoms, each of which is its own little magnet with a north and south pole. Just like we looked at electric fields, we also want to look at magnetic fields. The field lines in a magnetic field are based on the direction that the north pole of a compass needle would point if placed in the magnetic field. This means that magnetic field lines will point away from north poles and toward south poles. The magnetic field around a bar magnet looks like this. The magnetic field between the north pole of one magnet and the south pole of another magnet would look like this. The magnetic field between two north poles would look like this. And the magnetic field between two south poles would look like this. We can get much more complex magnetic fields than those surrounding bar magnets. For instance, the Earth has a magnetic field, and it is not as simple as the ones we just saw. Think back to Earth science. You learned about topographic maps. In a topographic map, the steepest part of a hill is where the lines are closest together. In this example, it would be the south side of the hill. In the map of a magnetic field, the field is strongest where the lines are closest together. In this map of the Earth's magnetic field, you can see the lines all converge up in Canada and down near Antarctica. Those 2 points are the north and south magnetic poles of the Earth, and that's where the magnetic field of the Earth is the strongest. The final unit of the year is modern physics. The first lesson is about the Bohr model of the atom. I'd like to start with the history of atomic theory. You don't have to write this down, but I think it's important that you hear it. Atomic theory originates in ancient Greece and India. Atomism is the belief that all matter is composed of discrete units that are indestructible and immutable. At the time, this is more of a philosophical idea and not a scientific principle. There isn't much advancement in atomic theory for over 2,000 years. In 1808, John Dalton proposes that each chemical element is composed of atoms of a single unique type. Almost 90 years later, J.J. Thomson discovers the electron, proving that atoms are not actually indivisible, but are made of positively and negatively charged components. This is often referred to as the plum pudding model. In 1909, Ernest Rutherford discovers that the positive charge of an atom is located in a small, compact nucleus surrounded by the negatively charged electrons. This comes from the famous gold foil experiment. In 1913, Niels Bohr accounts for shortcomings in the Rutherford model by restricting electrons to particular circular orbits of fixed energy. Finally, in 1926, Erwin Schrödinger describes the electron as a wave function rather than a point particle. This is often referred to as the electron cloud model. Before we can go much further, we have to talk about particle-wave duality. This is where you should start taking notes. In the Bohr model, electrons make transitions between energy levels by emitting or absorbing energy. This energy is in the form of a photon, and a photon is a particle of light. This might prompt you to ask, but isn't light a wave? Actually, it's both. There are many phenomena that involve light. A few of them are listed here. Some of these can be explained as light behaving like a wave. Others can be explained as light behaving like a particle. Reflection, refraction, interference, polarization, and diffraction can all be explained as light behaving like a wave. The new phenomenon of electron transitions cannot be explained if light is behaving like a wave. Reflection and refraction can also be explained as light behaving like a particle. However, light behaving as a particle cannot explain interference, polarization, or diffraction. Most importantly, the only way that we can explain electron transitions is as light behaving like a particle. Let's talk about electron transitions in the hydrogen atom. In the hydrogen atom, energy levels are numbered 1, 2, 3, 4, 5, and 6. When an electron absorbs a photon, the electron transitions to a higher energy level. When it emits a photon, it transitions to a lower energy level. Let's take a look at an example. This is a representation of the hydrogen atom with the electron in the energy level n equals 1. If it absorbs a photon, it will transition to a higher energy level. At this point, it could absorb another photon and go to some higher energy level. Eventually, it will emit this energy as a photon and return to n equals 1. This energy level diagram is another way to represent those energy levels. Let's take a look at some of the key parts of this diagram. On the left, you have the names of the levels. For the hydrogen atom, these are numbered. You'll see on your reference table that for the mercury atom, the energy levels are lettered. On the right, we have the energies of the levels. There are two important things to note. First of all, these energies are in units of eV. More about this later. Second, these energies are listed as being negative. The third important thing to note is that n equals 1 is considered the ground state. This is the only stable state. The electron can stay in the ground state forever. When the electron exists at a higher energy level, it will eventually transition back down. Finally, notice that the highest energy level above n equals 6 is called n equals infinity. This is known as the ionization level, and this represents that the electron has gained enough energy to escape the atom. That energy unit, eV, stands for electron volt. An electron volt is the amount of energy gained by an electron moving across a potential difference of 1 volt. Let's calculate it. Work equals potential difference times charge, and if we plug in 1 volt and the charge of the electron, we get a work of 1.6 times 10 to the negative 19 joules. This means that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. You should write this down in your notes, but keep in mind that this is also found on the front page of your reference tables. Let's talk a little more about the energy levels themselves. The energy of the levels represents the amount of energy required for an electron to become ionized from that level. Since the electron is basically missing this energy, it's described as being negative. Keep in mind that there's no such thing as negative energy. It's also important to note that electrons cannot exist between energy levels. They are either on n equals 1, 2, 3, 4, 5, 6, or they have gained enough energy to become ionized. This means that when an electron makes a transition, it must absorb or emit the perfect amount of energy. The energy of the photon involved in the transition is equal to the absolute value of the difference between the energy levels. The energy of a photon is directly proportional to its frequency. This relationship is apparent in the equation E photon equals hf. E photon is the energy of the photon, f is the frequency, and h is a constant known as Planck's constant. You can find this value on the reference table. It's 6.63 times 10 to the negative 34 joule seconds. You'll see this equation written in an additional form on your reference table. Since F is equal to c over lambda, the energy of the photon could also be equal to hc over lambda. Let's take a look at an example. I want to know what color is the photon that is emitted when the electron makes a transition from n equals 4 down to n equals 2. The first step is to determine the energy of the photon in electron volts. If we take the absolute value of the difference between 0.85 electron volts and 3.4 electron volts, we find that the energy of the photon in electron volts is 2.55. Next, we have to convert from electron volts to joules. To do this, we'll set up a proportion. 1 electron volt over 1.6 times 10 to the negative 19 joules equals 2.55 electron volts over x. We find that this energy in joules is 4.08 times 10 to the negative 19 joules. Next, we have to calculate the frequency of the photon. We know that the energy of the photon equals Planck's constant times the frequency. If we solve for the frequency, we get 6.15. If we solve for the frequency of the photon, we get 6.15 times 10 to the 14 hertz. Finally, we have to look up the frequency on the reference tables to determine what color this is. It's blue. The second lesson in modern physics is about energy-mass equivalence. In 1905, Einstein published a paper entitled, "Does the inertia of a body depend upon its energy content?" In that paper, he wrote, if a body gives off the energy L in the form of radiation, its mass diminishes by L divided by c squared. In other words, this means that energy and mass are equivalent to each other. We are more familiar with the idea of energy-mass equivalence in the form of the equation E equals mc squared, where E stands for energy, m stands for mass, and c is the speed of light in a vacuum. Let's take a look at a couple of examples of energy-mass equivalence. The first example we'll look at is nuclear fusion. Deuterium and tritium are isotopes of hydrogen. This means that they both have one proton, but differing numbers of neutrons. In the Sun, a deuterium atom and a tritium atom can be compressed by the incredible gravitational forces into a helium atom with a neutron left over. The mass of the helium and the neutron that we end up with is 3.13 times 10 to the negative 29 kilograms less than the deuterium and the tritium that we started with. How can we put two things together and end up with less mass? Well, this, quote, missing mass is released as energy. Let's calculate how much. If we plug in a mass of 3.13 times 10 to the negative 29 kilograms and multiply it by the speed of light in a vacuum squared, we get an energy of 2.8 times 10 to the negative 12 joules. This all by itself is not that much energy. But when you have this reaction happening many times all at once, you do get a lot of energy, such as in the Sun or in a nuclear explosion. In addition to using the equation E equals mc squared, there's also another way of finding the energy equivalent of a certain amount of mass, or the mass equivalent of a certain amount of energy. Since we're often dealing with very small masses, we sometimes use universal mass units instead of kilograms. One universal mass unit is equivalent to 931 mega electron volts. You can use this equality in a proportion. Let's take a look at an example. A uranium-236 atom will decay into a barium-141, a krypton-92, and 3 neutrons. The mass of the uranium is 0.01897 universal mass units more than the mass of the barium, krypton, and neutrons combined. I want to know how much energy in mega electron volts was released in this reaction. The first step is to set up a proportion. 1 universal mass unit over 931 mega electron volts equals 0.01897 universal mass units over x. If we cross multiply and divide, we get an energy of 17.7 mega electron volts. The final lesson in modern physics is about the Standard Model. The Standard Model of particle physics describes the elementary particles and the forces by which they interact. Elementary particles are the smallest constituents of matter. These particles are not composed of other smaller particles. These are truly the building blocks of the universe. There are two types of elementary particles. These are known as quarks and leptons. Quarks are elementary particles that combine to form composite particles known as hadrons. There are 6 what we call flavors or types of quarks. The first quarks discovered were the up and down quarks. The next 2 quarks to be discovered are known as the charm and strange quarks. The final quarks to be discovered are known as the top and bottom quarks. You can see that the up, charm, and top quarks all have a charge of positive 2/3 of an elementary charge, and the down, strange, and bottom quarks all have a charge of negative 1/3 elementary charge. Just because some of these particles have the same charge doesn't mean that they're the same. There are many other properties of particles. One very obvious one is mass. Although charm quarks have the same charge as ups, they're more massive, and top quarks are more massive still. Leptons are elementary particles that do not combine to form larger particles. There are also 6 flavors of leptons. There are the electron and the electron neutrino, the muon and the muon neutrino, and the tau and the tau neutrino. You can see that the electron, the muon, and the tau all have a charge of -1 elementary charge, and that all the varieties of the neutrino are neutral. Each quark and lepton has an associated antiparticle. Antiparticles have the same mass as the particle, but the opposite charge. And antiparticles use the same symbol as the particle, but they have a line drawn over it. For instance, we have the up quark with a charge of +2/3 elementary charge, and we have the anti-up quark, see the line, with a charge of -2/3 elementary charge. Now we can talk about the classification of matter. Anything in the universe that is not pure energy is matter. Matter can be divided into 2 main categories. The first is leptons, which we've already learned about. These are not made of anything smaller, and do not combine to form anything bigger. Then we have hadrons. Hadrons are particles that are composed of quarks. There are 2 types of hadrons. The first are known as baryons. All baryons are made of either 3 quarks or 3 antiquarks. The other type of hadron is known as meson. All mesons are made up of 1 quark and 1 antiquark. Let's take a look at a couple of very familiar examples of hadrons. Protons and neutrons are hadrons, and are only composed of up and down quarks. Let's take a look at the quark composition of the proton. In order to end up with the charge of the proton with which we are familiar, the proton must be composed of 2 up quarks and a down quark. This could be written as UUD, and this gives us +1 elementary charge. Now let's take a look at the quark composition of the neutron. A neutron is composed of 1 up and 2 down quarks. This could be written as up, down, down. And of course, we end up with a charge of 0. Finally, we have to mention the 4 fundamental forces of the universe. The weakest of the 4 forces is gravity, which is a natural phenomenon by which physical bodies attract each other with a force proportional to their masses. The force of gravity has an infinite range. The next strongest force is known as the weak nuclear force, and this is responsible for the radioactive decay of subatomic particles, and it initiates the process of hydrogen fusion in stars. The weak nuclear force has a very short range. The next strongest force is the electromagnetic force, which is responsible for the interaction of electrically charged particles and the interaction of magnetic fields with electrical conductors. The electromagnetic force has an infinite range. The final and strongest force is known as the strong nuclear force, which is responsible for the binding of quarks into hadrons, and the binding of hadrons, like protons and neutrons, into larger particles. The strong nuclear force has a short range.